The universe is massive. Billions of galaxies, each with billions of stars, stretching farther than our minds can grasp. But what if these giants collided? What would happen if the largest objects in the universe, galaxies, superclusters, even supermassive black holes crashed into each other with unimaginable force? Today, we're diving into a cosmic collision course, exploring the chaos, the energy, and the stunning transformations that could reshape the universe. Understanding the largest objects in the universe. Galaxies are the first step in understanding the largest objects in the universe. They are vast systems of stars, gas, dust, and dark matter, bound together by gravity. The Milky Way, our home galaxy, spans about 100,000 light-years across and contains roughly 100 to 400 billion stars. Its structure is defined by a dense central bulge surrounded by spiral arms, with a halo of dark matter extending even further. The nearest large galaxy, Andromeda, stretches around 220,000 light-years and contains over 1 trillion stars. Its mass is estimated to be roughly 1.5 times that of the Milky Way, and it moves toward our galaxy at about 110 kilometers per second. Observations show that galaxies are not static. Stars within them orbit the center at hundreds of kilometers per second, while gas clouds and dust interact dynamically, creating areas of star formation and regions of high-energy radiation. Spiral galaxies, elliptical galaxies, and irregular galaxies all vary in size, density, and stellar composition, but each represents a structure of immense scale and complexity. Beyond Andromeda, there are galaxies like IC 1101, which measures approximately 6 million light-years in diameter, making it one of the largest known galaxies, containing an estimated 100 trillion stars. Its sheer volume demonstrates that galaxies can vary by orders of magnitude in size, mass, and luminosity. These galaxies are not isolated. They are grouped into clusters, gravitationally bound systems containing hundreds to thousands of galaxies. The local group, for example, includes the Milky Way, Andromeda, the Triangulum Galaxy, and about 50 smaller dwarf galaxies, all spanning roughly 10 million light-years. The Virgo cluster is far larger, containing more than 1,300 galaxies within a radius of approximately 2 million light-years. The Coma cluster contains over 1,000 galaxies, stretching across nearly 20 million light-years. In these clusters, galaxies move relative to each other at thousands of kilometers per second. Observations in X-ray wavelengths reveal the presence of extremely hot gas trapped within the cluster, reaching temperatures of tens of millions of degrees and emitting X-rays detectable by telescopes like Chandra. Dark matter contributes a significant portion of the cluster mass, dominating the gravitational structure and determining the movement and interaction of galaxies within the cluster. Collisions between galaxies within clusters are common over cosmic timescales, producing tidal tails, streams of stars, and gas that are stripped or compressed, triggering star formation. Clusters themselves are components of larger structures called superclusters. The Laniakea supercluster, which includes the Milky Way, covers roughly 520 million light-years and contains an estimated 100,000 galaxies. Its mass is around 10 to the power of 17 solar masses, with gravity drawing all member galaxies toward a central point. Superclusters form interconnected networks linked by filaments of galaxies and gas, known collectively as the cosmic web. These filaments can extend for hundreds of millions of light-years and are composed primarily of dark matter, galaxies, and hot gas. Voids, large regions with few or no galaxies, exist between filaments, making the structure highly non-uniform. The cosmic web is revealed through mapping galaxy positions, redshifts, and gravitational lensing, allowing astronomers to visualize the distribution of matter on the larger scales. The interactions between clusters within superclusters are responsible for large-scale flows of matter, galaxy mergers, and shockwaves in intergalactic gas. processes observable with telescopes sensitive to X-rays, visible light, and infrared radiation. At the centers of most large galaxies are supermassive black holes. Sagittarius A star, at the center of the Milky Way, has a mass of 4.3 million times that of the Sun and a Schwarzschild radius of about 13 million kilometers. Observations using the Very Large Telescope and the Keck Observatory have tracked the orbits of stars near Sagittarius A star, providing precise measurements of its mass and confirming the presence of an event horizon. TON 618, one of the largest known black holes, has a mass of 66 billion solar masses and an estimated radius exceeding 1.9 billion kilometers. Its accretion disk emits enormous amounts of radiation, making it detectable across billions of light years. Supermassive black holes grow through mergers and accretion of matter, and their gravitational influence can dominate the dynamics of entire galaxies, affecting star orbits and galactic structure. When two supermassive black holes collide, the event releases gravitational waves of extraordinary intensity, propagating through space-time and detectable by instruments like LIGO and Virgo. Individual stars, while smaller than galaxies or clusters, can also reach enormous scales. Hypergiant stars such as VY Canis Majoris and UY Scuti represent some of the largest known stars by radius. VY Canis Majoris has an estimated radius of 1,420 solar radii, which would extend past the orbit of Jupiter if placed at the center of our solar system. Its mass is approximately 17 to 25 solar masses, with a luminosity around 300,000 times that of the Sun. WY Scuti exceeds 1,700 solar radii and emits roughly 340,000 times the Sun's luminosity. These stars are comparatively low density, with extended atmospheres where the outer layers are only a fraction of the density of Earth's atmosphere. They are unstable and lose mass rapidly through stellar winds, producing nebulae of gas and dust that expand into the interstellar medium. The end of their life cycles produces supernovae, or collapses into black holes, contributing to the chemical enrichment of their galaxies. Observations from Hubble and ground-based telescopes provide size estimates by resolving their angular diameters, while Chandra detects high-energy emissions from stellar winds and surrounding nebulae. James Webb adds detailed infrared measurements, allowing determination of surface temperatures, composition, and dust-enshrouded regions. Measuring galaxies, clusters, superclusters, black holes, and hypergiant stars relies on multiple observational techniques across the electromagnetic spectrum. Optical telescopes identify stellar populations and galactic structures. Radio telescopes map gas distributions. X-ray observatories reveal hot intergalactic gas and black hole activity. Infrared observatories penetrate dust clouds to uncover hidden regions of star formation. Redshift measurements indicate the velocities and distances of galaxies, revealing expansion and large-scale motion. Gravitational lensing allows mapping of dark matter by observing the distortion of background light, and spectroscopy determines chemical compositions and temperatures. Each object's mass, radius, luminosity, and density can be quantified, enabling astronomers to calculate gravitational effects, orbital dynamics, and potential energy released during interactions or collisions. Even within clusters and superclusters, the scales are staggering. A galaxy cluster spanning several million light-years contains more mass than 1 trillion suns, yet the distances between individual galaxies are often measured in hundreds of thousands of light-years. Superclusters extend hundreds of millions of light-years, and the cosmic filaments connecting them stretch for similar distances. Black holes at the centers of massive galaxies can influence stars thousands of light-years away. Hypergiant stars, while minuscule in comparison to galaxies, are millions of times larger than Earth and tens of thousands of times more luminous than the Sun. These numbers create a context where gravitational interactions and energy releasing collisions are beyond any scale observable in our solar system. And the physics governing such events is extreme, involving relativistic speeds, strong gravitational fields, and high-energy radiation. Every large object in the universe moves relative to others, creating potential for collisions over cosmic timescales. Galaxies orbit within clusters. Clusters move relative to each other within superclusters, and superclusters themselves shift slowly under the influence of gravity and the expansion of space. Hypergiant stars orbit galactic centers or exist in binary systems with extreme gravitational interaction. Black holes merge over millions or billions of years. Mapping these motions using redshift, proper motion measurements, and simulations allows astronomers to predict future collisions, such as the Milky Way-Andromeda merger or the eventual interactions between large clusters in the Laniakea supercluster. Each collision or merger redistributes mass, energy, and angular momentum, triggering phenomena like starbursts, gas shocks, and black hole accretion events. Observing, measuring, and modeling these objects relies on the integration of multiple data sources. Telescopes like Hubble provide optical imaging. Chandra detects X-rays from hot gas and black holes. JWST observes infrared signatures of star formation and dust. And radio arrays map gas clouds and dark matter through gravitational lensing effects. Supercomputer simulations reproduce galaxy and cluster mergers over billions of years, testing theories of structure formation and energy distribution. Each observation confirms that the universe is structured hierarchically, with galaxies forming clusters, clusters forming superclusters, and superclusters interconnected through the cosmic web, with black holes and hypergiant stars embedded within these structures. This hierarchy defines the larger scales of the universe and the objects that dominate its mass, energy, and gravitational influence. Beyond the vast assemblies of galaxies and clusters, the largest structures in the universe extend into the realm of supermassive black holes, hypergiant stars, and the intricate networks of the cosmic web. Each of these objects is measured with precision, and each reveals a scale and energy that is almost impossible to grasp. Tethys 618, for example, is not just a supermassive black hole, it is one of the most massive known objects in the universe, with a mass 66 billion times that of the Sun. Its event horizon alone spans billions of kilometers, a boundary where space itself curves into a singularity. The gravitational pull near this black hole is so intense that even light cannot escape. Detecting it requires analyzing the radiation emitted from its accretion disk, which shines with the brightness of over 10 trillion suns, visible across billions of light years. Observatories in space and on Earth track the spectral signatures of this light, measuring the velocity of matter spiraling inward and determining the mass with remarkable precision. The detection of such extreme objects has revolutionized our understanding of how galaxies grow and evolve, because these black holes regulate star formation, influence gas flows, and anchor the gravitational dynamics of entire galactic cores. Hypergiant stars are extreme in their own right. Atu-Uaiscuti, located roughly 9,500 light-years from Earth, is a red supergiant with a radius more than 1,700 times that of the Sun. Its outer layers extend over 2 billion kilometers, and its surface temperature is approximately 3,365 Kelvin. These stars are relatively low in mass density compared to smaller stars, yet their luminosity reaches hundreds of thousands of times that of the Sun, radiating energy across visible and infrared wavelengths. Observing these stars with telescopes like Hubble and JWST allows astronomers to determine the chemical composition of their atmospheres, measure the rate at which they lose mass through stellar winds, and study the structure of surrounding nebulae formed from ejected material. Hypergiants are rare, transient, and often located within star-forming regions of galaxies, and their life cycles provide critical insight into stellar evolution and the distribution of elements necessary for planet formation. Moving to the largest collective structures, superclusters such as the Laniakea supercluster form enormous gravitational basins. Laniakea spans roughly 520 million light-years, contains approximately 100,000 galaxies, and has a mass of around 10 to the power of 17 solar masses. The central point of attraction, called the Great Attractor, draws galaxies across hundreds of millions of light-years. Using redshift surveys and mapping peculiar velocities of galaxies, astronomers have traced how matter moves within this supercluster, revealing large-scale flows that are governed by gravitational forces extending far beyond individual clusters. Filaments connecting these superclusters form the cosmic web, a lattice of matter spanning the observable universe. These filaments are not merely concentrations of galaxies, but also contain diffuse gas and dark matter. Their existence is inferred through simulations, weak gravitational lensing, and the distribution of galaxies, showing how matter is channeled along vast strands, while enormous voids of near-empty space exist between them. Galaxy clusters themselves are dynamic environments. In clusters such as Coma or Abell 2744, galaxies are moving at speeds of up to 2,000 kilometers per second relative to one another. The intracluster medium, composed of hot plasma, reaches temperatures exceeding 100 million Kelvin and emits strongly in X-ray wavelengths. Collisions within clusters can strip galaxies of their gas, forming long trails of matter called tidal streams. These interactions trigger bursts of star formation in some regions while quenching it in others. Observations of these phenomena rely on multi-year wavelength data. Optical telescopes map star distributions, X-ray observatories detect the hot gas, radio telescopes identify synchrotron emissions from relativistic particles, and infrared instruments reveal dust-obscured star formation. Supermassive black holes influence their surroundings beyond the confines of their host galaxies. Their gravitational fields affect nearby star orbits, gas clouds, and dark matter halos. Observations of merging black holes, such as those detected by LIGO and Virgo through gravitational waves, indicate that when two black holes of millions or billions of solar masses collide, they release energy equivalent to the total energy output of hundreds of millions of galaxies for a fraction of a second. These events allow astronomers to probe the extreme limits of physics, testing general relativity and measuring the behavior of space-time under the most intense gravitational conditions known. Supermassive black holes also drive phenomena such as relativistic jets, where particles are accelerated near the speed of light and ejected across thousands of light years, heating surrounding gas and influencing star formation. Individual hypergiant stars and stellar clusters can affect their immediate regions through stellar winds and supernova explosions. VY Canis Majoris, for example, loses mass at a rate of around 10 to the power of -4 solar masses per year. This material forms complex structures of gas and dust that can stretch over multiple light years. When such a star ends its life, the resulting supernova can release more energy than the Sun will emit over its entire 10 billion year lifespan. The explosion not only contributes elements like carbon, oxygen and iron to the interstellar medium, but can also compress nearby gas clouds, triggering new star formation. Massive stars are thus key players in shaping the evolution of galaxies, distributing matter and energy over vast distances. The measurement of these objects requires precise instrumentation and techniques. Parallax measurements provide distances to nearby stars, while standard candles such as Cepheid variables and Type 1a supernovae allow distance estimates to galaxies and clusters millions of light years away. Spectroscopy reveals motion through Doppler shifts and the chemical composition of stars, galaxies, and interstellar gas. gravitational lensing maps dark matter by observing the distortion of light from background objects. High-energy observatories detect X-ray and gamma-ray emissions from black holes, supernova remnants, and clusters. Infrared telescopes penetrate dust, uncovering hidden star formation and mapping hypergiant stars in detail. Combining these techniques produces a complete picture of scale, mass, density, and energy distribution across objects that span millions to billions of light years. The velocity of these massive objects is as significant as their mass. Galaxies orbit cluster centers at thousands of kilometers per second. Clusters themselves move within superclusters, and filaments channel matter along gravitational paths across hundreds of millions of light years. Hypergiant stars rotate, pulsate, and eject material at hundreds of kilometers per second. Black holes orbit within galactic centers or merge over cosmic timescales. These motions create the conditions for interactions and collisions, shaping the large-scale structure of the universe. Predicting future encounters, like the eventual collision of the Milky Way and Andromeda, relies on detailed measurements of mass, velocity, distance, and gravitational influence, providing simulations of how objects on these scales will interact billions of years into the future. Each of these largest objects reveals the limits of density, gravity, and energy in the universe. Galaxies demonstrate how billions of stars can remain bound over hundreds of thousands of light years. Clusters show the effects of extreme gravitational binding on multiple galaxies and hot plasma. Superclusters reveal the organization of matter on scales of hundreds of millions of light years. Black holes concentrate billions of solar masses into regions smaller than our solar system, and hypergent stars radiate energy at hundreds of thousands of times the sun's output. These objects exist in constant motion, colliding, merging, and influencing one another, forming the foundation for understanding the dynamics and scale necessary to imagine what would happen if the largest objects in the universe were to collide. Observations, measurements, and simulations continue to expand our knowledge of these cosmic giants, mapping size, mass, and energy to give an accurate sense of the structures that dominate the universe. Cosmic collisions in history. The universe is in constant motion. Nothing sits still. Stars orbit their galaxies. Galaxies orbit clusters. Clusters move within superclusters, and everything is connected by gravity. On a human scale, the night sky looks calm and steady. But on cosmic scales, everything is moving at speeds and energies that are almost impossible to imagine. Collisions between galaxies and black holes are some of the most dramatic events in the universe, and astronomers have been observing them for decades, giving us a front-row seat to events that shape the cosmos. One of the most famous predicted collisions involves our own galaxy, the Milky Way, and the Andromeda galaxy. The two galaxies are approaching each other at roughly 110 kilometers per second, and current estimates suggest they will collide in about 4.5 billion years. Andromeda is almost twice the size of the Milky Way, containing over 1 trillion stars, while the Milky Way has between 100 and 400 billion. When they collide, it won't be a sudden crash like cars colliding on Earth. Instead, it will be a slow, drawn-out gravitational dance that takes millions of years. Stars themselves are too far apart to actually hit each other most of the time, but their gravitational interactions will distort the shapes of both galaxies. Spiral arms will stretch and twist. Gas clouds will compress, triggering massive waves of star formation, and eventually the two galaxies will merge into a single, giant elliptical galaxy. Astronomers have simulated this event using supercomputers, showing long tidal tails stretching millions of light years, streams of stars ripped from their orbits, and massive gas shocks lighting up in X-rays. Even though this is billions of years away, it gives us a glimpse of the kind of large-scale interactions that have shaped the universe over billions of years. Collisions like this aren't just theoretical. Astronomers have observed galaxy mergers across the universe, providing clear examples of what these events look like in real time. The antennae galaxies are a famous pair of colliding galaxies located about 45 million light-years away. They are named for the long, arching streams of stars and gas that resemble insect antennae, stretching tens of thousands of light-years from their centers. These galaxies are in the middle of a violent interaction, with their stars, gas, and dust clouds being pulled apart by gravity. Observations in multiple wavelengths, from visible light to X-rays, reveal bursts of new star formation where gas clouds collide and compress. Some of the most massive stars in these regions are forming at incredible rates, shining millions of times brighter than the Sun. Hubble has captured these images in extraordinary detail, showing the overlapping spirals, dense star clusters, and chaotic knots of gas and dust. These mergers demonstrate that collisions are not destructive in the sense of annihilation. Instead, they are transformative, reshaping galaxies, redistributing stars, and triggering bursts of activity that can last hundreds of millions of years. Further out, collisions can involve entire clusters of galaxies. In these scenarios, individual galaxies may not directly collide, but the hot plasma that fills the space between them interacts in explosive ways. The Bullet cluster is a famous example of two galaxy clusters that pass through each other at speeds of several thousand kilometers per second. Observations of the Bullet cluster in X-rays reveal hot gas being compressed and shocked, while gravitational lensing maps show how dark matter passed through largely unaffected. These events allow astronomers to study the distribution of matter on the larger scales and to test models of dark matter and gravity. Unlike galaxy-galaxy collisions, these cluster collisions release energy on scales billions of times greater than the most powerful supernova, demonstrating that collisions in the universe can involve energies far beyond anything that occurs within individual galaxies. Even more extreme are collisions between black holes, which are some of the densest objects in the universe. When two black holes merge, they release energy in the form of gravitational waves, ripples in space-time that travel at the speed of light across the cosmos. The first detection of such a merger was GW 150914, observed in 2015 by the LIGO Observatory. Two black holes, one about 36 times the mass of the Sun and the other 29, spiraled into each other, releasing energy equivalent to 3 solar masses in just a fraction of a second. That energy didn't come out as light or radiation, but as a distortion of space-time itself, travelling across 1 billion light-years before reaching Earth. These observations confirmed a major prediction of Einstein's general relativity and opened an entirely new way of observing the universe. Since then, dozens of black hole mergers have been detected by LIGO and Virgo, ranging from tens to hundreds of solar masses, some of which occur in distant galaxies billions of light-years away. Each detection provides information about how black holes form, how massive stars evolve, and how galaxies and clusters assemble over cosmic time. Collisions can also trigger visible fireworks, like gamma-ray bursts, which are among the brightest explosions in the universe. When massive stars collapse, or when neutron stars merge, the event can produce narrow jets of high-energy radiation detectable across billions of light-years. Observatories such as Swift and Fermi have captured these bursts, showing that collisions at small scales can produce radiation that outshines entire galaxies for seconds to minutes. In galaxy mergers, the compression of gas clouds can trigger bursts of star formation so intense that new star clusters form at rates thousands of times higher than in a typical galaxy. In some cases, collisions funnel gas toward the centers of galaxies, feeding supermassive black holes and creating active galactic nuclei, where the energy output can be millions of times greater than a normal galaxy. Observations of past collisions help us reconstruct the history of the universe. Many elliptical galaxies in the local universe are thought to be the products of ancient mergers, where spiral galaxies combined over billions of years. Streams of stars, shells of gas, and irregular distributions of old star clusters provide evidence of these events. By comparing simulations to observations, astronomers can determine the likely sequence of interactions that produce the galaxies we see today. Mergers leave fingerprints on both the structure and the motion of stars and gas. The study of these collisions shows that the universe is not static but constantly evolving, with interactions and mergers shaping its large-scale structure and driving the formation of new stars, planets, and black holes. The scale of these collisions is beyond human comprehension. Even the slow approach of the Milky Way and Andromeda involves hundreds of billions of stars interacting across millions of light-years. Cluster collisions span tens of millions of light-years, involving thousands of galaxies and clouds of gas heated to tens of millions of degrees. Black hole mergers concentrate masses greater than the Sun into regions no larger than our solar system and release energy on a scale that dwarfs the output of entire galaxies. Observing these events requires telescopes capable of capturing light across the electromagnetic spectrum, supercomputers to simulate dynamics over billions of years, and gravitational wave detectors sensitive to distortion smaller than a fraction of a proton's width. Each method adds a piece to the puzzle, allowing scientists to understand the scale, energy, and consequences of these extraordinary collisions. Even in deep space, Hubble has captured countless examples of galaxies merging. The Whirlpool galaxy, interacting with its companion NG C5195, shows tightly wound spiral arms distorted by gravitational forces. Star formation regions glow intensely in these areas, observable in ultraviolet and optical wavelengths. The antennae galaxies, already mentioned, provide a view of an ongoing collision where thousands of star clusters are forming simultaneously. Beyond visible light, infrared observations reveal dust-enshrouded regions where new stars are forming rapidly. These examples demonstrate that collisions are a common process, fundamental to the growth and evolution of galaxies across cosmic time. Every galaxy in the universe has likely undergone multiple collisions, and many will continue to merge in the future. Black hole collisions and galaxy mergers are not isolated events, but occur in hierarchical structures. Clusters of galaxies collide, funneling galaxies together and increasing the likelihood of mergers. Superclusters, connected by filaments, act as highways guiding the motion of galaxies and clusters over hundreds of millions of light-years. Simulations of these structures show that over billions of years, galaxies and black holes interact repeatedly, gradually reshaping the universe. Each collision redistributes mass and energy, creates new stars, triggers supernova, and alters the orbits of entire systems. Observations confirm that these processes are ongoing, providing both a record of the universe's history and a forecast of its future evolution. Gamma-ray bursts, or GRBS, are some of the brightest explosions we can observe. They can outshine entire galaxies for a few seconds or minutes, and astronomers first detected them in the 1960s while monitoring Earth for nuclear tests. Today, GRBS are observed by satellites like SWIFT and Fermi, which detect high-energy photons arriving from deep space. Many GRBS come from the collapse of massive stars, where the core implodes into a black hole and the remaining material is ejected in narrow jets at nearly the speed of light. Others come from neutron star mergers, as with GW170817. The energy released in a single gamma-ray burst can be equivalent to what our Sun emits over its entire 10 billion year lifetime, compressed into just seconds. Observing GRBS allows astronomers to study star formation in distant galaxies, understand how matter behaves under extreme pressure, and trace the expansion of the universe itself. Even though these events involve smaller objects like individual stars or binary systems, the energy they release is enough to influence their host galaxies, triggering shock waves, heating interstellar gas, and sometimes even disrupting nearby star-forming regions. Shock waves are another consequence of collisions on both small and intermediate scales. When galaxies collide, their interstellar gas clouds interact violently, creating pressure waves that travel through the material at thousands of kilometers per second. These shocks compress gas, initiating new waves of star formation while heating surrounding regions to millions of degrees. In clusters of galaxies, when two clusters pass through each other at several thousand kilometers per second, the shock waves in the intracluster medium produce X-ray emissions detectable by telescopes like Chandra and XMM Newton. Observations of the bullet cluster, for instance, show a bow-shaped shockwave extending for millions of light-years, caused by the collision of two massive clusters. This hot ionized gas moves faster than the galaxies themselves, and the energy involved is billions of times greater than the most energetic supernova. Shockwaves like these also serve as traces for the distribution of dark matter, because while gas interacts and slows down, dark matter continues largely unaffected, revealing the invisible structure that dominates the universe's mass. Even smaller collisions, such as star clusters merging or individual stars interacting in dense environments, can produce measurable effects. In globular clusters, stars orbit closely enough that gravitational interactions can lead to collisions or mergers, forming unusually massive stars or binary systems that emit X-rays. Planetary nebulae, remnants of dying stars, often show evidence of past interactions, where material expelled from one star is compressed or distorted by nearby companions. These events, while tiny compared to galaxy mergers, illustrate the same fundamental processes: gravity pulling objects together, energy being redistributed, and material being ejected into the surrounding environment. Observing these smaller-scale collisions gives astronomers models to understand what happens when the scale is increased to galaxies, or even clusters of galaxies. Galaxy mergers themselves show the effects of collisions on a larger scale. Hubble has captured dozens of interacting systems where tidal forces stretch spiral arms, gas clouds collide, and star formation is ignited at rates far higher than in isolated galaxies. The antennae galaxies, for example, contain thousands of new star clusters formed as the two galaxies pass through each other. In these interactions, gravitational torques funnel gas toward the centers of the galaxies, sometimes feeding central supermassive black holes, creating active galactic nuclei and triggering jets of particles that extend thousands of light years. These observations reveal that collisions do not simply destroy structures. They transform them, redistribute matter, and create bursts of energy visible across millions of light years. Shockwaves in these galaxy collisions are not limited to X-rays or visible light. Infrared and radio observations reveal massive clouds of cold gas being compressed, forming dense knots where stars ignite. In some cases, the collisions are so energetic that entire star-forming regions are expelled from the galaxies, creating streams of stars stretching hundreds of thousands of light years. These interactions demonstrate how energy flows from gravitational potential into kinetic and thermal energy, shaping the morphology of galaxies over hundreds of millions of years. Observing these processes allows astronomers to trace the history of galaxies, reconstruct past mergers, and predict future interactions, such as the eventual Milky Way-Andromeda merger. The consequences of these smaller collisions, whether they involve individual stars, star clusters, or galaxies, set the stage for understanding the largest collisions in the universe. Even a single gamma-ray burst can alter the composition of nearby regions, spreading heavy elements across hundreds of light years. Shockwaves from cluster mergers heat gas to tens of millions of degrees, affecting the dynamics of thousands of galaxies. Gravitational waves from black hole or neutron star mergers ripple across billions of light years, providing a direct probe of the universe's most extreme environments. When the scale increases to superclusters or massive black holes interacting, the energy released, the distances involved, and the gravitational forces are orders of magnitude greater. But the underlying physics is remarkably similar. Gravity pulls objects together. Kinetic energy is converted into heat, light, or gravitational waves, and matter is redistributed across the surrounding space. Observations across the electromagnetic spectrum are crucial for understanding these processes. Optical telescopes capture stars and galactic structures. X-ray observatories reveal hot gas and shock waves. Radio telescopes trace cold molecular clouds. And infrared instruments uncover star-forming regions hidden by dust. Gravitational wave detectors provide entirely new information about mergers that emit little or no light. Combining these methods gives a multi-dimensional picture of collisions at every scale, from the relatively small, like a neutron star merger in a distant galaxy, to the medium scale of interacting galaxies, to the extreme scales of clusters and superclusters. Astronomers can measure velocities, masses, energy output, chemical composition, and even the influence of dark matter in each interaction. Smaller collisions also show the timescales involved in cosmic interactions. Stars merge over thousands to millions of years. Star clusters evolve over hundreds of millions. And galaxy mergers take hundreds of millions to billions of years. Even when collisions are energetic, the effects can propagate for millions of light years, creating long-lasting consequences for their environment. Understanding these smaller-scale interactions allows astronomers to model how larger-scale events, like the collision of entire superclusters, might unfold over billions of years. They show how kinetic energy converts into radiation, heat, or gravitational waves, and how matter is redistributed through the cosmic web, forming the complex structure we observe today. How massive objects warp space-time. Gravity is the invisible force that governs everything in the universe, shaping the motion of stars, galaxies, and even the largest structures we can observe. When we talk about gravitational interactions on cosmic scales, we are not just talking about apples falling to the ground. We are talking about objects so massive that they bend the fabric of space and time itself. Einstein's general relativity tells us that mass warps space-time, creating what we perceive as gravity. The more massive an object, the deeper the well it creates. A star like the Sun produces a noticeable curvature in space, enough to keep planets in orbit. A black hole, millions or billions of times the Sun's mass, curves space-time to such an extent that not even light can escape. When massive objects move near each other, their gravitational fields interact, creating complex distortions that influence every particle, photon, and even space-time itself in their vicinity. On galactic scales, gravitational interactions become staggering. A galaxy like the Milky Way contains hundreds of billions of stars, interstellar gas, dust, and a dark matter halo that extends well beyond the visible edge of the galaxy. Its mass curves space-time around it, influencing nearby galaxies, satellite systems, and even objects in intergalactic space. When two galaxies approach each other, the gravitational forces between them are not uniform. They vary with distance, producing tidal effects that stretch and distort the galaxies. These tidal forces pull stars and gas into elongated streams called tidal tails. The tidal forces in a galaxy merger can extend over hundreds of thousands of light years, creating structures visible from millions of light years away. In some cases, entire spiral arms are twisted or ripped apart, while star clusters are ejected into intergalactic space. These effects are not sudden. They unfold over hundreds of millions of years, yet the energy involved is immense, constantly reshaping the structure of galaxies. Dark matter plays a crucial role in these gravitational interactions. Although it does not emit light, dark matter constitutes the majority of mass in galaxies and clusters. Its gravitational influence dominates how galaxies rotate and how clusters move. In collisions, dark matter interacts only gravitationally, passing through other dark matter halos largely unaffected, while visible matter, stars and gas, interacts through collisions, friction and shocks. Observations of colliding galaxy clusters, such as the Bullet cluster, show a clear separation between dark matter and normal matter. The dark matter continues along its path, creating gravitational wells that affect the motion of the visible matter and help map the unseen mass in the universe. Without dark matter, the tidal forces, orbital speeds, and eventual merger outcomes would be entirely different. Dark energy, on the other hand, acts as a repulsive force on cosmic scales, accelerating the expansion of the universe and influencing the frequency and timing of collisions over billions of years. It sets the stage on the larger scales, determining how quickly superclusters drift apart and how long it takes for massive structures to interact. The energy released in collisions at these scales is staggering. Even a single galaxy merger converts enormous amounts of gravitational potential energy into motion, heat, and radiation. Gas clouds compressed in collisions can ignite starbursts, regions where thousands of stars form simultaneously, releasing energy far beyond anything a single star can produce. The kinetic energy of stars moving in distorted orbits is converted into thermal energy when gas clouds collide, heating interstellar gas to millions of degrees. In clusters of galaxies, the energy involved can dwarf the output of individual supernovae by orders of magnitude. The Bullet cluster, where two clusters pass through each other at thousands of kilometers per second, generated shocks and turbulence in the gas, releasing energy equivalent to millions of supernova explosions. These shock waves propagate through the intracluster medium, accelerating particles to near light speeds and producing X-ray and radio emissions, detectable across millions of light years. Black hole mergers represent the extreme end of energy release. When two supermassive black holes spiral into each other, the gravitational energy released is far greater than the combined luminosity of all the stars in their host galaxies. The merging process distorts space-time violently, emitting gravitational waves that ripple across billions of light years. These waves carry energy that can exceed the output of hundreds of millions of suns over just a few seconds. Unlike radiation from stars or supernovae, gravitational waves interact very weakly with matter, traveling virtually unimpeded across the universe, providing a direct measurement of the dynamics of these collisions. LIGO and Virgo have detected dozens of such events, revealing black holes ranging from tens to hundreds of solar masses. Each detection not only confirms the presence of these objects, but also measures the energy involved in their mergers, giving astronomers a new way to quantify cosmic violence. Even smaller scale collisions produce extraordinary effects. When neutron stars collide, the energy release can rival the brightest gamma-ray bursts ever observed. Material is ejected at relativistic speeds, forming jets that extend for light years, and the collision synthesizes heavy elements like gold, platinum, and uranium. Observing these events allows astronomers to measure the amount of energy converted from gravitational potential into light and kinetic energy. Gamma-ray bursts associated with such collisions can be detected across billions of light years, and in some cases the energy output is equivalent to the total energy emitted by a galaxy over 1 billion years. These extreme processes show that gravitational interactions at all scales, stars, star clusters, galaxies, and black holes, transform potential energy into observable phenomena, shaping the universe and providing the foundation for understanding larger collisions. Tidal forces in galaxy mergers create structures that are both beautiful and destructive. Stars in the outer regions of galaxies experience weaker gravitational binding, making them more susceptible to being flung into intergalactic space. Gas clouds experience differential forces, compressing in some regions while stretching in others, creating localized bursts of star formation. In extreme cases, the central regions of galaxies can collapse inward, funneling gas towards supermassive black holes and igniting quasars that shine with the energy of trillions of suns. The combination of gravitational warping, tidal stretching, and energy release results in structures that can be observed billions of light years away, offering a record of cosmic evolution. Simulations of galaxy mergers show that these processes are inevitable when massive objects interact, and the morphology of the resulting galaxies depends on the mass ratio, orbital geometry, and gas content of the colliding systems. On the scale of clusters and superclusters, gravitational interactions operate over millions of light years, producing effects that dwarf anything within individual galaxies. When clusters collide, the gravitational potential energy involved can reach 10 to the power of 63 ergs or more. The intracluster medium, composed of hot plasma, interacts through shocks and turbulence, while galaxies themselves mostly pass through each other. These shocks accelerate particles to ultra-relativistic speeds, producing synchrotron radiation detectable in radio wavelengths. Observing these interactions allows astronomers to map the distribution of dark matter, trace the motion of gas, and measure the energy dissipated during collisions. The physics governing these events provides insight into how the largest structures in the universe form and evolve over billions of years. Dark matter influences tidal forces and energy release in ways that are subtle but profound. Because dark matter is collisionless, it passes through interactions unaffected by pressure or electromagnetic forces. Its gravitational influence, however, dominates the orbits of galaxies and the paths of gas during mergers. In simulations, removing dark matter entirely results in drastically different tidal structures, reduced energy release, and altered galaxy shapes after collision. Dark energy, while acting on much larger scales, controls the expansion of the universe, affecting how quickly massive objects can collide. Together, dark matter and dark energy set the cosmic stage for interactions, determining both the frequency and the intensity of collisions throughout cosmic history. Gravitational interactions are not just about motion. They convert potential energy into observable effects. In a galaxy collision, the kinetic energy of stars moving in distorted orbits heats gas clouds, triggers starbursts, and feeds central black holes. In black hole mergers, gravitational potential energy becomes gravitational waves. In neutron star collisions, it becomes light, kinetic energy, and heavy elements. The range of energy release spans orders of magnitude, from the equivalent of billions of suns in star-forming regions to more than 10 to the power of 54 ergs in the most violent black hole mergers. By comparing these energies to familiar benchmarks, solar output, supernovae, and gamma-ray bursts, it becomes clear just how extreme these processes are, even in smaller collisions. Every collision, no matter the scale, demonstrates the universe's ability to transform mass and gravity into energy and structure. Tidal forces, energy release, and gravitational warping are interconnected. When galaxies collide, the tidal stretching funnels gas inward, feeding black holes that release energy as quasars. Shock waves from colliding gas clouds propagate outward, compressing other clouds and triggering new star formation. Gravitational waves from compact object mergers propagate across the universe, carrying information about mass, energy, and motion. Dark matter shapes the gravitational wells in which all of these processes occur, while dark energy modulates the overall expansion and timing of collisions. Together, these forces and energies create a universe that is dynamic, constantly evolving, and marked by collisions at every scale. Observing these processes requires instruments capable of detecting a vast range of phenomena. Optical telescopes reveal stellar and galactic structure. X-ray observatories detect hot gas heated by tidal interactions. Radio telescopes trace relativistic particles in shock waves. Infrared instruments see through dust to observe starbursts triggered by collisions. Gravitational wave detectors measure the ripples in space-time caused by black hole and neutron star mergers. Gamma-ray satellites capture the most energetic bursts of light from distant collisions. By combining these observations, astronomers can quantify the gravitational forces, tidal effects, and energy release involved, building a detailed picture of how massive objects interact and transform the universe around them. Even in smaller scale interactions, the effects of gravitational warping are evident. Star clusters in dense environments experience internal tidal forces, causing stars to migrate or merge. Binary star systems exchange mass and energy, sometimes producing novae or X-ray binaries. Collisions between molecular clouds trigger star formation, redistribute angular momentum, and inject turbulence into the interstellar medium. These processes, when scaled up, explain how galaxies, clusters, and superclusters behave during massive collisions. The physics is consistent across scales. Gravity drives motion, mass concentration produces energy, and tidal forces shape structure. What happens when supermassive black holes collide? The universe has its quiet moments, but then there are the moments that make everything tremble, bend, and ripple across billions of light years. Imagine two objects so massive that their gravitational pull dominates entire galaxies, each containing millions or even billions of times the mass of our Sun, spiraling toward each other over millions of years. These are supermassive black holes, lurking in the centers of galaxies, and when they collide, the universe itself seems to shudder. Space-time, the very fabric of reality, stretches and compresses in ways that were unimaginable until the first gravitational waves were detected. This isn't science fiction. This is happening across the cosmos, shaping galaxies, lighting up the sky, and creating gravitational symphonies that travel across the universe at the speed of light. When two supermassive black holes begin their cosmic dance, it starts slowly. Each black hole is surrounded by an accretion disk, a swirling maelstrom of gas, dust, and stars being pulled into orbit. These disks glow brilliantly in X-rays and infrared as friction heats the material to millions of degrees. As the black holes spiral closer, their gravitational fields interact, stretching and warping the space between them. Stars caught in these regions experience chaotic orbits, and gas clouds are compressed, triggering bursts of star formation in areas where nothing new might have ignited for millions of years. The tidal forces are unimaginable. Entire star clusters can be ripped from their galaxies, flung into intergalactic space, while jets of plasma are redirected by the gravitational tug-of-war. Observations of galaxies with multiple central black holes show us the signatures of these interactions, with warped disks, disturbed star formation regions, and unusual X-ray emission signaling that two giants are circling each other, slowly getting closer. The energy involved is staggering. Even before the actual collision, the spiraling motion of two supermassive black holes releases energy in the form of gravitational waves. These are ripples in space-time, stretching and compressing the fabric of the universe as the black holes orbit faster and faster. When they finally merge, the release is cataclysmic. Imagine 1 billion suns converted directly into gravitational waves in just seconds. These waves ripple outward, passing through galaxies, clusters, and interstellar space. For centuries, this energy would remain invisible to us if it weren't for detectors like LIGO and Virgo, which are designed to measure distortions far smaller than an atom. Even so, detecting waves from supermassive black holes requires new generations of instruments like the planned space-based LISA observatory, capable of sensing the slow, massive undulations produced by these colossal mergers. Each collision tells a story about mass, spin, and energy, revealing how the largest objects in the universe grow and interact. Accretion disks do not simply vanish when black holes merge, they collide and combine in spectacular fashion. The disks, already orbiting at thousands of kilometers per second, begin to interact violently as the black holes draw near. Gas and dust are compressed and heated, igniting emissions across the electromagnetic spectrum. X-rays flare as the innermost regions accelerate toward the newly forming singularity. Jets of plasma, often visible for tens of thousands of light years, may change direction, becoming brighter or splitting into multiple streams as the gravitational field rearranges itself. Observing these flares allows astronomers to understand the dynamics of merging disks, the behavior of matter near event horizons, and the processes that feed the growth of the new, more massive black hole. Some of the energy released is so intense it can heat surrounding gas to millions of degrees, producing shock waves detectable across intergalactic space. The consequences of these collisions are felt long after the black holes have merged. Galaxies are reshaped, their structure twisted and redistributed by the gravitational ballet of the central giants. Spiral galaxies may lose their ordered arms, becoming elliptical or lenticular. Gas clouds funnel into the galactic center, fueling further star formation and feeding the black hole itself. The influx of material often creates active galactic nuclei, quasars, that shine with the energy of trillions of suns, visible across billions of light years. Observing quasars at different stages allows astronomers to reconstruct the history of black hole mergers, seeing how the energy from these central engines propagates through the galaxy, triggers waves of star formation, and alters galactic morphology. Star formation triggered by black hole collisions is intense and dramatic. Gas clouds pulled inward by gravitational interactions compress, becoming dense enough to collapse into new stars. In some regions, this process produces thousands of stars over tens of millions of years, creating bright clusters visible even in distant galaxies. The distribution of these new stars can be irregular, reflecting the chaotic gravitational forces of the merger. Some clusters form in arcs and streams that trace the path of the black holes, leaving a record of the interaction for astronomers billions of years later. Infrared observations reveal these young, hot stars, while X-ray and radio emissions highlight the feedback processes as radiation and stellar winds sculpt surrounding gas, shaping the galaxy's future evolution. The growth of black holes themselves is a direct consequence of these collisions. Each merger creates a more massive singularity, increasing the gravitational pull at the galactic center and influencing the motion of surrounding stars. The central black hole can reach masses of tens or even hundreds of billions of solar masses after repeated mergers. These hypermassive black holes dominate their host galaxies, stabilizing the orbits of stars while continuing to accrete gas from the surrounding environment. The process is self-reinforcing. More mass means stronger gravitational pull, which attracts more material, which in turn triggers more star formation and radiation. Observations of massive elliptical galaxies and quasars in the early universe suggest that repeated black hole mergers were common, helping to form the largest known structures in the cosmos. The gravitational waves emitted in these collisions are not just a spectacular display. They are messengers, carrying information about the mass, spin, and orbital dynamics of the colliding black holes. Space-time ripples encode the entire history of the interaction, from the first close approach to the final merger. Scientists can reconstruct the orbit, measure the mass ratio, and even determine the alignment of the spins. This information allows us to test general relativity under conditions far beyond anything possible on Earth. In some cases, the merged black hole can experience a recoil, being kicked at thousands of kilometers per second by asymmetric gravitational wave emission. This recoil can displace the black hole from the galactic center, sending it wandering through space and altering the dynamics of the surrounding stars and gas. Observing collisions of supermassive black holes also provides insight into the evolution of galaxies. Galaxy mergers trigger black hole mergers, which in turn influence star formation, galactic morphology, and chemical enrichment. Some of the most massive galaxies we see today, often elliptical in shape, are the result of repeated mergers over billions of years. The collisions redistribute angular momentum, funnel gas toward the center, and generate shock waves that travel across the galaxy. These processes leave observable signatures, tidal tails, disrupted star clusters, active galactic nuclei, and large-scale jets of plasma. Each signature is a clue, allowing astronomers to piece together the history of galactic interactions and the role of black holes in shaping the universe. The interplay between accretion disks, jets, and surrounding stars is a story of energy transformation. Material spiraling into the black hole converts gravitational potential energy into heat, light, and kinetic energy. Some of this energy escapes as X-rays and gamma rays, while relativistic jets carry energy far beyond the galaxy itself, impacting neighboring galaxies and intergalactic gas. Shockwaves from these jets compress gas clouds, triggering additional star formation in regions that might otherwise remain dormant. Observations of jet-fed star formation in active galaxies reveal the enormous influence that black hole collisions can have on environments tens of thousands of light years away from the galactic center. Even before the actual merger, the gravitational pull of approaching black holes distorts the orbits of nearby stars, creating chaotic paths and sometimes ejecting stars into intergalactic space. In some cases, these interactions produce hypervelocity stars, flung at thousands of kilometers per second, speeding away from their galaxies. These stars carry a record of the gravitational forces that ejected them, and by studying their trajectories, astronomers can infer the history of the black hole interaction that created them. The scale of influence is immense. The collision of two supermassive black holes can reshape an entire galaxy, alter star formation patterns, trigger active nuclei, and inject energy into intergalactic space. Accretion disks themselves can produce luminous flares as they merge. When the disks collide, turbulence and shocks heat material to extreme temperatures. Gas clouds spiral inward, forming temporary hotspots that shine across multiple wavelengths. X-ray telescopes, like Chandra and NuSTAR, observe these flares, mapping the dynamics of the disks and revealing how matter behaves in the presence of extreme gravity. Some models suggest that these flares can be so bright that they rival the luminosity of a galaxy, creating a temporary but extraordinary light show visible across cosmic distances. The final moments of a black hole merger are a crescendo of gravitational and electromagnetic energy. As the event horizons merge, gravitational waves peak, carrying away mass energy equivalent to millions or billions of suns. The newly formed singularity stabilizes, often with a spin determined by the combination of the progenitor black hole's masses and orientations. Gas, dust, and stars in the vicinity respond to the new gravitational potential, forming new accretion structures and adjusting their orbits. The galaxy continues to evolve, forever marked by the collision that shaped its core, triggered new generations of stars, and grew its central black hole to unimaginable size, hypothetical collisions of the largest known objects. Imagine two of the universe's most massive objects on a collision course. Not stars, not galaxies, but entire clusters of galaxies, each containing hundreds or thousands of galaxies, trillions of stars, massive clouds of hot gas, and dark matter halos that stretch for millions of light years. One of the most extreme examples we've studied is the El Gordo cluster, located over 7 billion light-years away. Its name means the fat one in Spanish, and it's not hard to see why. El Gordo isn't just big, it's enormous, more than 3 quadrillion times the mass of the Sun, and it's not alone. In a hypothetical collision with another similarly massive cluster, the energy released would make anything on smaller scales, from galaxy mergers to supernovae, look minuscule. When galaxy clusters collide, the first thing that happens is a slow but immense gravitational pull. These clusters are moving at speeds of several thousand kilometers per second, and as they approach, their gravitational fields interact. Galaxies within each cluster mostly pass through each other without direct collision, because the distances between stars are so vast. But the gas filling the space between galaxies, plasma at tens of millions of degrees, does collide. This intergalactic gas is compressed, creating shock waves that ripple through the clusters at speeds comparable to supernova ejecta, but on scales tens of millions of times larger. These shocks heat the gas even further, generating X-ray emissions that we can detect across billions of light-years. Observing these emissions with instruments like Chandra and XMM Newton allows astronomers to map the collision in astonishing detail, revealing the turbulence, temperature variations, and dynamics of these cosmic giants. The shock waves are huge in scale. Imagine a wave moving through a medium thousands of times the size of our galaxy. These shock fronts can stretch for millions of light-years, compressing gas clouds along their path. The heating isn't uniform. Some regions reach temperatures exceeding 100 million degrees Kelvin. In these zones, atoms are stripped of their electrons, forming a fully ionized plasma. The X-ray radiation from this plasma can outshine the combined light of all the galaxies in the clusters. These emissions provide a kind of cosmic fingerprint, letting scientists reconstruct the timing, speed, and trajectory of the collision. They can see which parts of the clusters have collided head-on, which portions have passed by, and where the gas is lagging behind the dark matter, which moves through largely unaffected. Dark matter plays a critical role in these collisions. While the hot gas interacts violently, slowing down and producing shock waves, the dark matter halos of each cluster pass through one another almost undisturbed. Observations of El Gordo and other clusters show a clear separation between visible matter and dark matter during collisions. By mapping gravitational lensing effects, astronomers can visualize where the unseen mass is located. This separation not only provides direct evidence for the existence of dark matter, but also influences the dynamics of the collision. Galaxies and gas are drawn toward these invisible wells, stretching tidal tails and forming complex patterns that can last for billions of years. In some cases, the dark matter distribution can even affect where new star formation occurs in the aftermath, funneling gas into dense knots that ignite bursts of stellar activity. The kinetic energy involved in these collisions is almost unimaginable. Galaxy clusters contain thousands of galaxies, each with hundreds of billions of stars, plus enormous amounts of hot gas and dark matter. When clusters collide, the gravitational potential energy converts into kinetic energy, heating gas, and accelerating particles. In El Gordo, simulations suggest that the collision energy is on the order of 10 to the power of 63 ergs, billions of times more energetic than a supernova. This energy drives the shock waves, compresses gas clouds, and triggers turbulence that persists for hundreds of millions of years. The result is not just a mess of hot gas, it's a cosmic storm of unprecedented scale, shaping the clusters and their galaxies long after the initial encounter. As the clusters pass through each other, the intergalactic gas is slowed and disrupted, while the galaxies continue relatively unaffected. This leads to striking observational features. In some collisions, the gas is left trailing behind, forming long tails or bow-shaped structures that glow brightly in X-rays. Meanwhile, the dark matter continues along its path, guiding the motion of galaxies and influencing the eventual gravitational settling of the clusters. Simulations of El Gordo show how these interactions can twist and stretch the gas into arcs and filaments, creating shock-heated regions visible across hundreds of thousands of light years. These features are more than just dramatic. They encode information about the speed, mass, and geometry of the collision, allowing astronomers to reconstruct events that happened billions of years ago. Collisions of this scale can also trigger the formation of new galaxies. As gas clouds compress in shock fronts, they can collapse under their own gravity, forming dense stellar nurseries. Over millions of years, these nurseries coalesce into new galaxies or massive star clusters. In addition, the compression of gas can feed central supermassive black holes, igniting quasars that shine with the luminosity of trillions of suns. The combined X-ray and radio emissions from these processes create a multi-wavelength signature that astronomers can track across cosmic distances. Observing cluster collisions is like watching a slow-motion explosion, where the aftermath continues to evolve for billions of years, producing light, heat, and gravitational effects visible long after the initial impact. The dynamics of cluster collisions are also influenced by the angle of impact. A head-on collision produces intense shocks and symmetric structures, while an off-center encounter creates swirling patterns, twisted gas filaments, and asymmetrical distributions of galaxies. In simulations of El Gordo, the best matches to observations come from slightly off-center collisions, where one cluster grazes the other, sending shockwaves racing through the gas, while the dark matter halos pass through mostly intact. These scenarios show how sensitive the dynamics are to initial conditions, and how the enormous scale of clusters magnifies even small differences in approach velocity or angle. Every collision is unique, leaving behind a signature that astronomers can decipher to understand the past motion of these titanic systems. X-ray emissions are perhaps the most dramatic visible consequence of cluster collisions. The plasma in the intergalactic medium is heated to millions of degrees, producing continuous X-ray radiation. Observatories like Chandra capture these emissions, showing the hot gas stretched into arcs, filaments, and bow shocks. These images reveal not only the intensity of the collision, but also the temperature distribution and density of the gas. In El Gordo, the X-ray observations show a shock front moving at thousands of kilometers per second, with gas temperatures exceeding 100 million degrees. The data allows scientists to calculate the energy released, the speed of the collision, and even the distribution of dark matter. The hot gas can remain turbulent and X-ray bright for hundreds of millions of years, long after the galaxies themselves have settled into a new configuration. Magnetic fields are also stirred during these collisions. As shock waves move through the plasma, they amplify magnetic fields, accelerating charged particles and producing synchrotron radiation visible in radio wavelengths. Observations of radio relics in colliding clusters provide a complementary view to X-ray emissions, showing how particles are energized over millions of light years. These radio features often outline the shock fronts, giving astronomers a three-dimensional view of the collision dynamics. The combination of X-ray and radio data allows scientists to build detailed models of the energy transfer, turbulence, and particle acceleration occurring during these massive cosmic events. Gravitational lensing provides another window into cluster collisions. As the cluster's mass bends light from more distant galaxies, astronomers can map the distribution of both visible and dark matter. In El Gordo, lensing shows that the dark matter and hot gas are offset from each other after the collision, confirming that dark matter interacts only through gravity. This separation also explains why galaxies often continue moving relatively unaffected while the gas is slowed and heated. By combining lensing maps with X-ray and radio observations, astronomers can reconstruct the collision in 3 dimensions, seeing how the massive clusters moved, merged, and reshaped their environment over billions of years. Simulations play a crucial role in understanding these collisions. Supercomputers model the motion of galaxies, gas, and dark matter, incorporating gravity, hydrodynamics, and even magnetic fields. For El Gordo, simulations show that the observed X-ray emissions, shock fronts, and galaxy distributions can only be reproduced by a nearly head-on collision at extremely high velocities. These models allow scientists to test hypotheses about the mass, speed, and trajectory of the clusters, as well as the properties of the intergalactic gas. They provide insight into the long-term evolution of the system, predicting how the clusters will eventually settle into a more stable configuration, how shockwaves will dissipate, and where new galaxies and star clusters might form. The scale of these events is almost impossible to comprehend. A shock front stretching millions of light years, heating gas to hundreds of millions of degrees, accelerating particles to near light speed, and producing X-ray and radio emissions across billions of light years. The total energy involved surpasses anything produced by galaxy mergers or supernovae by orders of magnitude. Galaxy clusters colliding are not just larger, they are a different category of cosmic violence, where the forces of gravity, gas dynamics, and dark matter interplay on the grander scales, shaping the universe. Superclusters colliding. The universe is unimaginably huge, but then you start thinking bigger than galaxies, bigger than clusters, and you reach something that defies any sense of scale: superclusters. These are the largest known structures in the universe, vast chains of galaxy clusters bound together by gravity, stretching for hundreds of millions of light years, threaded along filaments of dark matter and intergalactic gas. Now imagine 2 of these massive structures on a collision course. This isn't just huge, it's beyond anything humans can truly grasp. We're talking about energy so vast they make even galaxy collisions look like a gentle breeze. No telescope has ever seen a supercluster collision in real life. It's purely hypothetical. But the physics tells us that if it happened, it would reshape everything in its path, bending space-time, heating gas, and sending shockwaves racing across cosmic filaments. Superclusters contain hundreds or even thousands of galaxy clusters, each packed with hundreds of billions of stars, hot gas, and dark matter. The space between clusters is far from empty. It's filled with tenuous plasma and connected by long, invisible cosmic filaments, channels of matter that stretch like highways across the universe. In a collision, the gravity of each supercluster would pull on everything in the other, twisting these filaments, pulling clusters out of alignment, and warping the shape of space itself. Gas between the clusters would collide first, creating huge shock waves that travel at thousands of kilometers per second, heating the intergalactic medium to temperatures far higher than any cluster collision. These shocks would be visible in X-rays across billions of light years, turning the collision into a spectacular cosmic light show. The energy released in such a supercluster collision is hard to imagine. Galaxy collisions already produce enormous amounts of heat, starbursts, and X-ray radiation. Cluster collisions go even further, with trillions of solar masses interacting and shockwaves compressing gas to extremes. Supercluster collisions would be on an entirely new level. Tens of thousands of clusters, each with their own galaxies, gas and dark matter halos, would interact. The gravitational potential energy alone would dwarf anything else in the universe. Gas would be stripped from clusters, compressed in enormous sheets, and heated to hundreds of millions of degrees. Entire filaments could vibrate, stretching and twisting under the pull of gravity. The energy released could rival the combined output of every star in every galaxy for billions of years, all happening in a single, slow-motion cosmic crash. Dark matter would be a silent player in this epic scenario. Unlike gas and galaxies, which collide, compress, and heat, dark matter would pass through almost unaffected, continuing along its path due to its collisionless nature. But its gravity would still shape the motion of visible matter, pulling gas and galaxies into new patterns. In simulations of large-scale structure formation, we see how dark matter forms scaffolding for filaments, clusters, and superclusters. A collision of two superclusters would tug violently on this scaffolding, bending filaments, compressing some regions while stretching others, and redistributing matter over hundreds of millions of light years. It's a cosmic dance on a scale that's almost impossible to picture, but its effects would ripple across the universe, affecting star formation, cluster dynamics, and the motion of galaxies for billions of years. Shock waves in a supercluster collision would be truly huge. In cluster collisions, we see bow shocks stretching millions of light years, heating gas to tens of millions of degrees, and producing X-ray emissions detectable across billions of light years. Supercluster collisions would magnify this by orders of magnitude. Shock fronts could stretch across hundreds of millions of light years, compressing gas along cosmic filaments and creating massive turbulence. These shock waves would move through the intergalactic medium like waves in a cosmic ocean, stirring filaments, triggering star formation in previously quiet regions, and altering the motion of entire clusters. If observed, the X-ray signatures alone would dwarf anything we currently know, lighting up huge portions of the universe with hot plasma and energetic particles. The filaments themselves would be profoundly affected. These cosmic highways of gas, dark matter, and galaxies connect superclusters, directing the flow of material across the universe. During a collision, gravity would twist and stretch these filaments like taffy. Some regions would be compressed, funneling gas and galaxies toward cluster intersections, igniting new star formation on unimaginable scales. Other parts would be pulled apart, creating voids and leaving trails of galaxies in unusual orbits. The collision would shake the cosmic web, rearranging matter along paths that could take billions of years to stabilize. Essentially, the universe's large-scale structure would be temporarily in chaos, bending under the influence of forces far beyond anything humans can experience. Energy transfer in these collisions would also affect galaxy evolution. As clusters collide and gas is heated and redistributed, galaxies within them would feel tidal forces strong enough to warp their shapes, strip away gas, and trigger bursts of star formation. Spiral galaxies could become elliptical over billions of years. Star formation might ignite in previously dormant galaxies, and supermassive black holes at cluster centers would suddenly have huge amounts of material funneled toward them. These collisions would accelerate the growth of black holes, ignite quasars, and produce jets that extend hundreds of thousands of light years. Every part of the superclusters, stars, gas, dark matter, black holes, would be pulled into a colossal, multi-layered interaction, producing light, heat, and gravitational ripples across unimaginable distances. Imagine the gravitational waves from such an event. Individual black hole mergers produce detectable ripples in space-time. Cluster collisions might produce very low-frequency gravitational waves detectable by future observatories, but supercluster collisions could produce ripples on scales so vast that they would subtly distort space-time across hundreds of millions of light years. The waves would move through the cosmic web, tugging on filaments, clusters, and even the voids between them. While they wouldn't be noticeable to humans directly, they would carry the signature of one of the most energetic events in the universe, providing a new kind of cosmic record for astronomers to decode. The collision process would take billions of years. Superclusters are huge, and even at speeds of several thousand kilometers per second, it would take enormous time for them to fully interact. The first contact would produce the initial shocks in the gas and filaments. Over hundreds of millions of years, the clusters within each supercluster would begin to interact, with tidal forces warping galaxies and funneling gas into cluster centers. After billions of years, the collision would settle, leaving behind a new, larger supercluster or a disrupted arrangement of clusters and filaments. The aftermath would be visible across the universe in X-rays, radio waves, and the distribution of galaxies. Jets from supermassive black holes in cluster centers would also be affected. As the superclusters collide, the gas funneled toward these central black holes could ignite enormous quasar activity. Jets could extend across millions of light years, interacting with shocked gas and compressed filaments. Observations of smaller-scale cluster collisions show how these jets heat gas, trigger star formation, and redistribute material. On supercluster scales, the effect would be amplified tremendously, impacting vast regions of intergalactic space. The cosmic web, the vast network of filaments connecting clusters and superclusters, would temporarily vibrate under the impact. Material would be rearranged along filaments, with gas and galaxies pulled into new streams. Shockwaves moving through these filaments would compress gas and potentially trigger star formation in previously quiet regions. The distribution of dark matter, largely unaffected by the collision, would continue to anchor the structure, but visible matter would be dramatically reshaped, creating regions of high density and enormous voids in the cosmic web. Simulations of supercluster collisions are purely hypothetical, but they offer a glimpse into the scale of energy involved. Models suggest that the total energy released would be orders of magnitude higher than any cluster collision ever observed. Shockwaves could reach hundreds of millions of light years in length, heating gas to extreme temperatures. Filaments would be stretched, compressed, and twisted, and galaxies within clusters would feel tidal forces strong enough to reshape them. Dark matter would guide the motion of visible matter, while the energy transfer would ignite star formation, feed supermassive black holes, and produce emissions across the electromagnetic spectrum. Even gravitationally, the impact would be enormous. Clusters moving through each other would pull on neighboring structures, altering orbits and redistributing matter across the supercluster. Filaments could be tugged out of alignment, dark matter halos could shift, and entire clusters might be ejected from their original paths. The gravitational influence of such a collision would be detectable across hundreds of millions of light years, affecting not just the colliding superclusters, but also nearby structures, subtly altering the evolution of the cosmic web. X-ray emissions would dominate our view of the collision. Hot gas in the clusters and filaments would glow brightly, producing enormous amounts of X-rays visible across billions of light years. Observatories sensitive to these energies would detect vast shock fronts, regions of compressed and heated plasma, and the turbulence left in the wake of the collision. In addition to X-rays, radio waves from accelerated charged particles in magnetic fields would trace the shock waves moving through filaments, offering another view of the energy transfer and particle acceleration occurring on these huge scales. Supermassive black holes colliding. Two supermassive black holes on a collision course is one of the universe's most extreme events. Each black hole can weigh millions or billions of times the Sun. When they spiral toward each other, the forces involved are beyond comprehension. The closer they get, the faster they move, orbiting each other at speeds approaching the speed of light. Space around them stretches and bends, and the gravity warps everything nearby. This is not just a local effect. It's a tidal pull that influences the motion of nearby stars, gas, and even entire clusters of stars. As they collide, energy explodes outward in the form of gravitational waves. These waves ripple through space, stretching and compressing the fabric of reality across billions of light years. For a brief moment, the energy released can be equivalent to billions of suns converted directly into motion of space-time. LIGO and Virgo detect smaller black hole mergers in our galaxy, but supermassive black hole collisions would generate waves detectable across the observable universe. Future space-based detectors like LISA will allow scientists to track these waves, reading the mass, spin, and orbit of the colliding giants. Each ripple carries a record of the collision, a map of forces so huge that ordinary matter cannot resist. The collision transforms the black holes. They merge into a single hypermassive black hole, far heavier than either one alone. Its gravitational pull dominates the galactic center, drawing in stars, gas, and even other black holes over millions of years. Accretion disks around each black hole combine violently, heating gas to millions of degrees and producing X-rays and gamma rays visible across billions of light years. Powerful jets can shoot out, carrying energy and matter across the galaxy, sometimes affecting neighboring galaxies. The merger reshapes the center of the galaxy, triggering star formation in compressed gas clouds, while altering the orbits of stars caught in the gravitational chaos. The final black hole can spin rapidly, depending on the angle and speed of the collision. Sometimes the merger produces a gravitational kick, sending the new hypermassive black hole moving through the galaxy at thousands of kilometers per second. Gas clouds and stars near the center are flung into chaotic orbits, while the black hole continues to grow, feeding on gas and smaller black holes captured by its immense gravity. Observing these collisions allows astronomers to understand how the largest black holes form and how they influence the galaxies that host them. Shockwaves from the merger travel through surrounding gas, heating it and producing intense radiation. These shockwaves can trigger bursts of star formation in gas clouds across hundreds of light years. In some cases, gas is funneled into the black hole, powering a quasar that shines with the energy of trillions of suns. These emissions can last millions of years, creating a bright beacon visible across cosmic distances. The collision not only grows the black hole, but also reshapes the galaxy, redistributing gas, accelerating stars, and producing radiation that travels across the universe. Gravitational waves continue to propagate outward long after the merger. They carry information about the masses, spins, and motion of the black holes before they collided. By detecting these waves, scientists can reconstruct events billions of years in the past, tracing how hypermassive black holes formed and how they affected their host galaxies. The universe vibrates with these collisions, a low-frequency hum that spans enormous distances, linking galaxies and clusters in a chain of gravitational echoes. Supermassive black hole collisions are rare, but the consequences are profound. They create the heaviest black holes in existence, produce waves that ripple across billions of light years, ignite quasars, reshape galaxies, and influence star formation. They are the engines that build the largest structures in the universe, the invisible powerhouses behind some of the brightest lights we see in the sky. Each collision leaves a mark on the cosmos, a transformation so extreme that the universe itself cannot ignore it. Hypergiant stars colliding. The universe has stars and then it has monsters. Hypergiant stars are the absolute giants of stellar life. Think of VY Canis Majoris or UY Scuti, stars so huge that if you put them in the center of our solar system, they would swallow Saturn, Jupiter, maybe even the Sun. Now imagine two of these colossal stars on a collision course. This is not a gentle crash. This is a cosmic explosion waiting to happen. When hypergiants collide, the energy released is so huge, it can outshine an entire galaxy for a brief moment. Simulations show that when two hypergiant stars merge, their outer layers slam into each other at thousands of kilometers per second. Gas, dust and plasma mix violently, creating shock waves that expand outward. These shock waves are like ripples in a pond, but on scales tens of billions of times larger. Computer models predict that the temperatures in the collision zone can reach billions of degrees, stripping atoms of all electrons and creating a plasma so hot it glows across X-ray and gamma-ray wavelengths. These are not just bright flashes. They are cosmic lighthouses visible across interstellar distances, capable of impacting nearby star systems with intense radiation. Depending on the mass of the colliding stars, the end result can be catastrophic. In some cases, the merged star becomes unstable and explodes as a supernova, sending a shock wave racing through surrounding space at thousands of kilometers per second. These explosions eject huge amounts of material, seeding the surrounding interstellar medium with heavy elements, iron, gold, uranium, that will one day become planets, moons, and even life. If the mass is high enough, the core can collapse directly into a black hole, a point so dense that not even light escapes. In the process, the collision can create gamma-ray bursts, beams of radiation so powerful they can travel across billions of light-years, threatening nearby star systems with lethal doses of high-energy photons. Computer simulations have made these collisions vivid. Using supercomputers, scientists model how two hypergiant stars interact when their envelopes touch. The models show twisting plasma flows, jets of material flung into space, and shock-heated regions glowing in X-rays. The cores may spiral together, rotating faster and faster as gravity pulls them inward, until they merge into a single object or collapse into a black hole. The surrounding material forms an accretion disk that can feed the newly formed black hole for thousands of years, producing radiation that lights up the galaxy. These simulations also reveal the chaotic magnetic fields generated during the collision, accelerating charged particles to near the speed of light and contributing to the gamma-ray bursts. Gamma-ray bursts from hypergiant collisions are among the most energetic phenomena in the universe. Short bursts last less than 2 seconds, but pack more energy than our Sun emits in its entire lifetime. Long bursts, triggered by massive stellar mergers, can last minutes, blasting nearby interstellar space with lethal radiation. Simulations show that these bursts are tightly collimated, forming narrow jets that travel across billions of light-years. Any star system in the path of the jet could have its planets irradiated, atmospheres stripped, and chemistry altered. In dense star clusters, a single hypergiant collision can trigger chain reactions, influencing the evolution of nearby stars and forming new pockets of star formation in compressed gas clouds. The formation of black holes in these events is equally dramatic. When the cores of hypergiants collapse, the gravitational pull becomes enormous, creating a singularity surrounded by an accretion disk of infalling material. The disk spins, heating up to millions of degrees, generating X-rays and gamma rays. Magnetic fields twist and shoot relativistic jets perpendicular to the disk, carrying energy far beyond the original collision site. Simulations show these jets can extend for thousands of light years, injecting energy into surrounding interstellar gas and even triggering the collapse of nearby clouds into new stars. The universe rearranges itself on a local scale, all because two colossal stars met and merged. Shockwaves from these collisions travel at extreme speeds, compressing nearby gas clouds and stirring turbulence. This turbulence can last for hundreds of thousands of years, influencing star formation long after the initial event. Dense pockets of gas can collapse into new stars, while other regions are blasted into low-density voids. Computer models visualize this as rippling sheets of gas, folding and twisting under the energy of the explosion. X-ray and gamma-ray maps from simulations show glowing filaments tracing the path of shockwaves through the stellar neighborhood. The scales are almost impossible to imagine. clouds of gas spanning light years, collapsing and heating under forces billions of times stronger than anything on Earth. Not all collisions lead to explosions. In some cases, hypergiant stars merge into an even larger, unstable star. These monsters can undergo pulsations, shedding mass in repeated bursts, radiating energy across the electromagnetic spectrum. Over millions of years, these stars lose enough mass to either stabilize temporarily or eventually collapse into a black hole. Simulations allow scientists to track the mass loss, radiation output, and eventual collapse, predicting when and where gamma-ray bursts or supernovae might occur. Observing nearby hypergiants provides clues, but the simulations bring the full-scale collision to life, showing the violent motions, glowing plasma, and shockwave propagation in exquisite detail. The radiation from hypergiant collisions also interacts with interstellar chemistry. Gamma rays and X-rays ionize gas, altering the formation of molecules like hydrogen, carbon monoxide, and water. Nearby dust grains are vaporized or restructured, changing the composition of the interstellar medium. These effects influence where future stars and planets form, and what elements are available in young stellar systems. In dense star clusters, a single hypergiant collision can leave ripples felt over dozens of light years, changing the destiny of thousands of stars. Magnetic fields are twisted and amplified during the collision. Charged particles accelerated along these fields produce synchrotron radiation, visible in radio wavelengths. Observations of supernova remnants and gamma-ray bursts in our galaxy hint at these processes, but hypergiant collisions amplify them on a scale millions of times larger. Simulations reveal intricate filaments of magnetic energy spiraling out from the collision site, guiding jets of plasma and shaping the path of ejected material. These fields also affect the formation of new stars, funneling gas into dense knots that collapse under gravity. Even gravity itself is stretched to its limits. As the cores merge, the warping of space-time generates gravitational waves, faint ripples travelling through the galaxy. For the most massive hypergiant collisions, these waves could be strong enough to be detected by future space-based observatories, offering a direct measurement of the event. Combined with X-ray, gamma-ray, and radio observations, scientists could reconstruct the entire collision, from the first contact to the collapse of the final black hole, giving unprecedented insight into the physics of extreme stars. Hypergiant collisions are rare but transformative. Each event creates a supernova, a black hole, or a gamma-ray burst that can dominate the light of an entire galaxy for brief moments. Shockwaves reshape nearby gas clouds, trigger star formation, and alter magnetic fields. Jets of plasma and radiation extend for thousands of light years, impacting star systems that might never have existed otherwise. Simulations show these events in stunning detail, revealing how energy moves, how matter interacts, and how the universe responds to the most extreme stellar encounters. These collisions are not just explosions, they are engines of creation and destruction. Heavy elements formed in the merger seed future generations of stars and planets. Black holes born in the collision can merge again, feeding larger structures. Gamma-ray bursts carve paths through interstellar space, sometimes sterilizing regions, sometimes compressing gas into new stars. On a cosmic scale, hypergiant collisions shape the evolution of galaxies, clusters, and the interstellar medium. They are violent, brief, and yet incredibly influential, leaving a mark that lasts for billions of years. How we detect massive collisions. When we talk about massive collisions in the universe, we're talking about events so enormous that it's hard to even imagine them. Entire galaxies smashing together, clusters of galaxies ripping through one another, black holes merging in the heart of distant galaxies, and stars so huge that their death shakes space-time itself. Detecting these cosmic catastrophes isn't easy. These events happen over millions or billions of years, often billions of light years away. Yet astronomers have developed ways to catch them, measure them, and even simulate them on supercomputers. The story of how we observe these collisions is a journey across the universe, from tiny ripples in space-time to glowing clouds of X-ray light, and to fully immersive computer models that recreate the chaos in astonishing detail. Let's start with gravitational waves, the ripples in space-time that carry the signature of some of the universe's most extreme collisions. When black holes collide, when neutron stars smash into one another, or when other massive objects merge, the energy of the collision is so huge that it actually distorts the fabric of space itself. These distortions travel outward at the speed of light, moving across billions of light years until they reach Earth. Detecting them requires incredibly sensitive instruments. That's where LIGO and Virgo come in. LIGO, the Laser Interferometer Gravitational Wave Observatory, is a set of giant detectors in the United States. And Virgo is a similar detector in Italy. They are basically enormous laser measuring sticks, each arm stretching kilometers long, capable of detecting changes in length smaller than a proton. When a gravitational wave passes through, it stretches one arm while squeezing the other, and this tiny change is enough to signal a collision billions of years old. The first detection in 2015 changed everything. LIGO captured the merger of two black holes over 1 billion light-years away, sending waves of space-time rippling across the detectors. Suddenly, the universe had a new kind of telescope, one that could feel the vibration of the cosmos. Since then, dozens of black hole and neutron star mergers have been recorded, each carrying information about mass, spin, and distance. These detections don't just tell us that collisions happened, they allow scientists to map the distribution of black holes across the universe, understand how they form, and even predict how massive structures grow over cosmic time. But gravitational waves are just one part of the story. For events involving galaxies, galaxy clusters, or stars, we rely on light across the electromagnetic spectrum. Telescopes like Hubble, Chandra, and the James Webb Space Telescope, JWST, allow astronomers to see the glow of intergalactic gas, the flash of supernovae, and the after effects of collisions. Hubble, orbiting above the atmosphere, captures visible and ultraviolet light in stunning detail, revealing galaxies in the process of merging, stretching, and twisting under tidal forces. The antennae galaxies, a famous pair of colliding galaxies, show long streams of stars and gas ripped out into space. Observing such systems allows scientists to see how stars form, how gas clouds interact, and how galaxies are reshaped by collisions. Chandra, an X-ray observatory, takes this a step further. Gas in clusters and galaxies can be heated to tens or hundreds of millions of degrees during collisions, producing X-rays that travel across space. Chandra can capture these high-energy photons, mapping shock waves and hot gas as galaxies slam into one another. Observations of cluster collisions, like the Bullet cluster, show gas lagging behind dark matter, revealing how the invisible scaffolding of the universe behaves during these massive events. JWST, with its infrared sensitivity, can peer through dust and gas, capturing the formation of stars triggered by collisions. Infrared light allows astronomers to see into the densest regions of merging galaxies, where starlight is otherwise hidden, showing bursts of star formation that would be invisible in optical light. To understand the full story, astronomers rely heavily on simulations. Massive collisions happen over millions or billions of years, and no telescope can watch them in real time. Supercomputers allow scientists to recreate these events virtually, using the laws of physics to predict how stars, gas, galaxies, and dark matter will behave. These simulations are staggering in complexity. They track billions of particles, including stars, gas clouds, and dark matter components and calculate gravitational interactions, hydrodynamics, and even magnetic fields. The result is a virtual universe where collisions can be paused, sped up, or observed from any angle. Scientists can test different scenarios. What happens if two clusters collide head-on versus off-center? How dark matter behaves when gas is slowed? Or how star formation ignites under tidal forces? NASA and ESA create visualizations from these simulations that are almost cinematic. They turn raw data into stunning images and animations, showing galaxies stretching into long tidal tails, gas clouds colliding and forming shock-heated filaments, and black holes merging with jets shooting out material across space. These visualizations aren't just beautiful, they are scientific tools. They allow researchers to compare simulations with real observations from telescopes, testing whether the models match reality. When a simulation reproduces the X-ray emissions, gravitational lensing patterns, or visible tidal structures of observed collisions, scientists gain confidence that their understanding of cosmic physics is correct. Simulations also provide insight into things that cannot be observed directly. For example, dark matter doesn't emit light, so its distribution in collisions is invisible. By simulating collisions with and without dark matter, astronomers can predict how galaxies and gas should behave if dark matter exists in certain ways. Observing the actual universe then allows them to test these predictions. In galaxy cluster collisions, simulations show that gas slows down due to friction, while dark matter passes through, creating the offset seen in systems like the bullet cluster. This kind of modelling allows us to explore phenomena that are otherwise hidden, giving a complete picture of cosmic collisions. The combination of detection, observation, and simulation is what makes modern astrophysics so powerful. Gravitational waves tell us that a collision happened and carry information about the masses and motion of objects involved. Telescopes across the electromagnetic spectrum capture the aftermath, the glowing gas, starbursts, and reshaped galaxies. Supercomputers allow us to reconstruct the entire event, filling in the gaps and providing a full three-dimensional understanding. Together, these tools transform abstract physics into something we can see, measure, and even visualize, bringing collisions across billions of light years into a form our human minds can comprehend. Observations are constantly evolving. New telescopes, more sensitive detectors, and faster supercomputers allow us to see smaller details, detect fainter signals, and simulate more complex scenarios. LIGO and Virgo are being upgraded, increasing their sensitivity to fainter gravitational waves, while space-based detectors like LISA will expand detection to even larger, slower waves from supermassive black hole mergers. Hubble continues to capture stunning images of galaxy mergers, while JWST reveals previously hidden star formation, and Chandra maps X-ray emissions with extraordinary precision. Each new observation adds a piece to the puzzle, refining simulations and allowing astronomers to explore collisions in ways that were impossible just a few decades ago. Simulation also allows scientists to explore extreme hypotheticals. What happens if two superclusters collide? How does a hypergiant star collision trigger gamma-ray bursts? By modelling these scenarios, researchers can predict the behaviour of matter and energy on scales that can never be tested experimentally. They can watch virtual universes evolve, colliding galaxies forming tidal tails, shockwaves moving through gas, and black holes merging and producing gravitational waves. These models are continuously refined by real-world observations, creating a feedback loop where theory and observation push each other forward. Even visualization has become an art form. NASA, ESA, and other organizations turn simulation data into cinematic sequences that feel like traveling through the universe. Galaxies stretch, twist, and glow, shockwaves ripple across intergalactic gas, and jets of plasma from black holes extend across space. These visualizations allow not only scientists, but also the public to experience the scale, power, and beauty of cosmic collisions. They show that collisions are not just explosions, they are dynamic, evolving, and beautiful processes that shape the universe on every scale. Detecting massive collisions, observing their effects, and simulating them on supercomputers is how we understand the cosmos. Without gravitational wave detectors, we would miss the ripples of black hole mergers. Without telescopes, we wouldn't see the glow of hot gas, the stretching of galaxies, or the after effects of cosmic collisions. Without simulations, we couldn't reconstruct the full story, test hypotheses, or explore extreme scenarios beyond observation. Together, these tools allow humanity to explore events that are billions of light years away, unfolding over millions of years, and to bring them into the realm of human understanding. Recent gravitational wave events discoveries. The universe has a way of surprising us, revealing events we never even imagined. In the last decade, astronomers have caught cosmic collisions in ways that were once purely theoretical. The first of these discoveries shook the foundations of astronomy. Gravitational waves from GW1 50914. In 2015, LIGO detected ripples in space-time that came from two black holes colliding over 1 billion light-years away. Scientists could measure the masses of each black hole, the speed at which they spiraled together, and the energy released. It was like feeling the heartbeat of the universe itself, a direct message from a collision that had happened eons ago. The energy released in those few seconds was more than all the stars in the observable universe produce, combined in that same span, a mind-blowing amount that literally warped the fabric of space-time. Gravitational wave detections didn't stop there. Each new event tells a story. Black holes of different sizes merging, neutron stars colliding and creating kilonovae, and hints of even larger, more exotic mergers yet to be fully understood. GW170817, for example, involved a neutron star collision, producing both gravitational waves and a flash of light across the spectrum, from gamma rays to visible light. Observatories around the world coordinated, capturing the afterglow, mapping how the debris expanded, and confirming that heavy elements like gold and platinum were created in the explosion. These events are not just numbers on a chart, they are cosmic fireworks, showing the immense power of collisions and giving scientists real-time insight into physics that was once only theoretical. Meanwhile, telescopes across the electromagnetic spectrum have caught galaxy clusters colliding. The Bullet cluster is one of the most famous examples. Observations in X-rays revealed gas clouds heated to tens of millions of degrees, ripping through one another as two clusters collided at thousands of kilometers per second. Meanwhile, the gravitational lensing of background galaxies showed that dark matter passed through unaffected, leaving the hot gas behind. This discovery didn't just provide a snapshot of a collision, it offered a direct view of dark matter in action, the invisible scaffolding of the universe guiding the visible cosmos during one of the most violent events imaginable. Other clusters followed. Observatories like Chandra, Hubble, and more recently JWST have captured collisions with stunning clarity. The El Gordo cluster, for example, is a massive, high-speed collision between galaxy clusters. X-rays map the shock-heated gas, while gravitational lensing reveals the hidden mass of dark matter. Simulations based on these observations show how the clusters will continue to interact over billions of years, stretching filaments, compressing gas, and triggering star formation on massive scales. Each observation adds pieces to the puzzle, letting astronomers compare what simulations predict with what actually happens in the cosmos. These discoveries also give a sense of scale that is hard to grasp. Galaxy clusters contain hundreds of galaxies, trillions of stars and enormous clouds of gas and dark matter. Collisions between these clusters release energy far beyond anything humans experience. Shock waves can stretch millions of light years. Gas is heated to incredible temperatures, and dark matter moves silently, guiding the galaxies through the chaos. Observing these events is like peeking into the most extreme physics laboratory in the universe, one that operates on scales billions of times larger than anything on Earth. Each new discovery pushes the boundaries of what we know. Gravitational waves have opened a new window, allowing scientists to detect collisions invisible in light. X-ray and infrared telescopes reveal the aftermath of collisions, showing the heating, compression, and star formation triggered by these cosmic events. Computer simulations bring the processes to life, helping us understand how dark matter and visible matter interact, how galaxies merge, and how energy moves through the largest structures in the universe. The combination of observation and simulation turns abstract physics into something visual and tangible, showing us collisions as both violent and beautiful, shaping the universe across billions of light years. Recent discoveries also hint at events we cannot yet see. Observatories continue to detect gravitational waves from mergers we haven't imaged in light, suggesting collisions involving black holes in distant galaxies, potentially hypermassive black holes forming in the cores of merging clusters. X-ray surveys continue to find hot gas in unusual distributions, indicating past collisions that reshaped clusters long ago. Each discovery adds to the story of how massive structures evolve, how energy is transferred, and how the universe continues to grow and change in ways we are only beginning to understand. The beauty of these discoveries is that they connect different parts of the cosmos. Gravitational waves from black hole mergers tie into the behavior of galaxies in clusters. Colliding clusters observed in X-rays give context to the gravitational interactions seen in simulations. Together, these discoveries reveal that the universe is not static, but dynamic, constantly reshaped by collisions at every scale, from stars to superclusters. Each new detection tells us about the past, helps us understand the present, and allows us to predict how the universe will evolve in the future. The collision impacts on our universe. When massive objects collide in the universe, the effects are immediate and enormous, far beyond anything we experience on Earth. The moment of impact releases an almost unimaginable amount of energy. Stars, galaxies, clusters, and even superclusters store gravitational energy on scales billions of times larger than our Sun. And when they crash together, all of that energy is suddenly unleashed. Gas clouds are heated to millions or even billions of degrees. Shock waves ripple through the cosmic medium, and entire regions of space light up with radiation spanning from radio waves to X-rays and gamma rays. These collisions are not quiet. They are fireworks that stretch across millions of light years, reshaping the cosmos with every second. Shock waves are the first visible effect of most cosmic collisions. When galaxy clusters slam into each other, gas in the clusters collides first. Unlike stars and dark matter, which mostly pass through, gas interacts violently, creating massive shock fronts that expand outward at thousands of kilometers per second. Observatories like Chandra have captured these shock waves in stunning X-ray images, showing bright, hot gas streaked across millions of light years. These shock waves don't just heat gas, they stir turbulence, compress clouds, and send ripples through the intergalactic medium. In simulations, the shock fronts look like glowing sheets of plasma, bending and stretching under the influence of gravity, pushing nearby galaxies and clusters into new arrangements. The energy contained in these shock waves is colossal, enough to influence the motion of entire galaxy clusters over billions of years. At smaller scales, when stars collide or massive black holes merge, the energy release can be even more intense in a localized region. Hypergiant star collisions produce supernova, gamma-ray bursts, and jets of matter accelerated to near-light speeds. Black hole mergers generate gravitational waves that ripple across billions of light years, carrying energy equivalent to billions of suns. The immediate effect is a violent rearrangement of matter in the local neighborhood, with stars thrown into new orbits, gas clouds heated, and radiation flooding space. In galaxy collisions, tidal forces stretch spiral arms into long streams of stars and gas, while in cluster collisions, the intracluster medium is compressed and heated. Every collision leaves a fingerprint, a dramatic mark of energy moving through the cosmos. Star formation bursts are one of the most visible consequences of these collisions. When gas clouds are compressed by shock waves or gravitational tidal forces, the density rises and new stars ignite. Galaxy collisions are famous for triggering these bursts, where thousands of stars can form simultaneously in a previously quiet region. Observations of systems like the antennae galaxies show brilliant knots of young, blue stars formed from gas compressed in the collision. Simulations reveal how shock waves travel through filaments and clouds, concentrating material and causing chain reactions of star formation across millions of light years. The bursts aren't just brief flashes, they seed entire regions of space with new stars, shaping the structure and evolution of galaxies for billions of years. At the scale of galaxy clusters, shock waves and star formation combine on an enormous scale. As clusters collide, gas compressed in the core can trigger star formation in central galaxies, while also generating X-ray radiation across the cluster. The surrounding filaments of gas experience turbulence, forming smaller pockets of stars far from the cluster centers. This process is visible in both simulations and observations. Hot X-ray gas glows as shock waves ripple outward, while new stars appear along compressed filaments and tidal tails. The immediate effects are chaotic and brilliant, a cosmic storm of energy, motion, and light, visible across the universe. Even dark matter, though invisible, plays a critical role in these impacts. During collisions, dark matter continues to move largely unaffected, guiding the motion of galaxies and gas clouds through gravity. This creates offsets between gas and dark matter, visible in systems like the bullet cluster, where the shock-heated gas lags behind the dark matter. The mismatch between what we see and what is invisible affects how energy is distributed, shaping shock waves and star formation in ways that are still being studied. Without dark matter, the impact patterns would look very different, with gas and stars following more predictable paths. Its silent presence amplifies the energy effects, bending the flow of matter across millions of light years. Computer simulations give us a closer look at these immediate effects. Supercomputers model collisions with billions of particles representing stars, gas, and dark matter, calculating how energy moves, how shock waves expand, and how stars ignite. Visualizations from NASA and ESA show galaxies stretching into long tidal tails, shock fronts glowing in X-ray light, and regions of intense star formation sparking across filaments. Simulations also reveal turbulence in gas clouds that lasts millions of years, showing that the immediate effects of a collision aren't just a brief flash, they ripple through the universe, reshaping structure and motion for eons. Energy release in these collisions is almost impossible to comprehend. A single galaxy cluster collision can produce more energy than all the stars in the Milky Way, combined over millions of years. Black hole mergers send gravitational waves carrying more energy than billions of suns. Hypergiant star collisions create gamma-ray bursts that momentarily outshine entire galaxies. This energy doesn't just vanish. It interacts with the surrounding medium, heating gas, compressing clouds, and igniting new stars. Observing these effects gives astronomers insight into the life cycle of galaxies, clusters, and even the universe itself. Shockwaves aren't limited to clusters. In supermassive black hole mergers, the jets from accretion disks plow through surrounding gas, generating shocks that compress clouds, trigger star formation, and redistribute energy across the galactic center. In hypergiant star collisions, gamma-ray bursts propagate through interstellar space, ionizing gas, stripping atmospheres from nearby planets, and reshaping molecular clouds. Every type of collision, whether star, black hole, galaxy, or cluster, produces waves of energy that cascade through space, interacting with everything in their path. Star formation triggered by these events can be dramatic. In some systems, thousands of new stars ignite simultaneously in compact regions, forming bright clusters visible across the galaxy. In others, shockwaves compress gas over millions of light years, causing bursts of star formation along filaments or tidal tails. This process can continue for millions of years, long after the initial collision, reshaping the stellar population and creating new structures in galaxies. Observations of colliding galaxies reveal these regions as bright knots of young, massive stars, often surrounded by glowing gas, heated by their radiation. The immediate effects of collisions also influence chemical evolution. Supernovae triggered by star formation release heavy elements like iron, gold, and uranium into surrounding gas. Gamma-ray bursts and black hole jets energize interstellar clouds, altering their chemistry and affecting the next generation of stars. Over time, these collisions enrich galaxies and clusters with elements essential for planet formation, creating the building blocks for future solar systems. In this way, the immediate energy release from collisions sets off a chain reaction that shapes not just the structure, but also the chemistry of the universe. Visualizations from supercomputer simulations show shockwaves moving like ripples through cosmic gas, forming filamentary patterns, compressing gas clouds, and igniting bursts of star formation. Galaxies stretch and twist, stars are thrown into new orbits, and black holes feed on surrounding matter. The combination of energy release, shockwaves, and star formation creates a universe in motion, a dynamic, ever-changing cosmos where collisions are the engines of transformation. Even the largest collisions, like clusters smashing into each other, follow these patterns. Gas heats, shockwaves travel across millions of light years, and stars are born in compressed regions. Dark matter guides the motion of galaxies and gas, while jets from supermassive black holes and gamma-ray bursts add bursts of energy into the mix. The immediate effects are visible in X-ray, infrared, and optical light, captured by telescopes and matched by computer simulations that reproduce every detail of motion, compression, and heating. The long-term effects of massive collisions. Massive cosmic collisions don't just explode and vanish. They leave fingerprints on the universe that last for billions of years. When galaxies smash together, their stars, gas, and dark matter slowly reorganize, reshaping the very structure of the galaxy over millions of years. Spiral arms twist and stretch, forming long tidal tails of stars and gas flung into space. Central regions can collapse into denser cores, feeding supermassive black holes and triggering bursts of star formation. The collisions set galaxies on entirely new paths, determining how they will grow, merge, and interact in the future. Observations of nearby galaxies show remnants of past collisions, elongated streams, chaotic cores, and bright clusters of young stars marking regions where gas was compressed and new stars ignited long after the initial impact. At even larger scales, when black holes merge, they shape the evolution of galaxy clusters. A hypermassive black hole born from a merger dominates the gravitational center of its galaxy, pulling stars and gas toward it. Over time, it influences the orbits of nearby galaxies within the cluster, guiding the motion of billions of stars. Jets from the black hole inject energy into the surrounding gas, preventing some regions from collapsing and forming stars while compressing others, creating pockets of new star formation. Over millions to billions of years, these effects change the very distribution of galaxies in a cluster, carving out voids, heating gas, and dictating where the next generation of galaxies will grow. Simulations of galaxy and cluster collisions show these long-term effects in vivid detail. Filaments stretch across hundreds of thousands of light years, hot gas slowly cools and condenses, and dark matter continues to steer the motion of stars and galaxies. Black hole mergers create ripples that last for eons, subtly influencing the movement of matter throughout the cluster. Shockwaves from the original collisions fade, but the energy they released has already set the stage for the next billion years of evolution. Structures that form during these events, tidal tails, star clusters, and galaxy cores, remain, shaping how the universe looks far into the future. Could these collisions affect life on Earth? Directly, probably not. We are far away from the kind of extreme events that could reach our planet with destructive force. But indirectly, the radiation from hypergiant star collisions, gamma-ray bursts, or the most energetic black hole mergers could be detectable across galaxies. A gamma-ray burst aimed in our direction, even from tens of thousands of light years away, could impact planetary atmospheres, stripping ozone or affecting chemical balances temporarily. The chances are tiny, but the fact that we can detect such radiation shows the immense reach of these cosmic events. They remind us that while life on Earth is protected from direct destruction by the vastness of space, the universe is constantly alive with events of staggering energy, echoing across billions of light years. Long-term effects of collisions are also cumulative. Galaxies that have merged once are more likely to collide again in the future. Clusters with multiple black hole mergers will see their central galaxies dominated by hypermassive black holes, reshaping star formation and the motion of nearby galaxies. Over cosmic time, the universe evolves through countless collisions, each building on the last. The patterns we see today, the shape of spiral galaxies, the distribution of clusters, the chemical composition of stars, are the result of billions of years of these violent interactions. Every collision leaves a legacy, energy redistributed, stars born and destroyed, galaxies transformed, and clusters reorganized. Even the light we see today carries the echoes of past collisions. Observing distant galaxies is like looking back in time, watching the long-term consequences unfold over billions of years. Streams of stars stretching across space, massive black holes feeding quietly in galactic centers, clusters of galaxies arranged along cosmic filaments. All of these are traces of past collisions, the fingerprints left by immense energy and gravitational chaos. Space is not static. It is shaped by the motion and interaction of its largest objects, and what appears calm today is the result of unimaginable violence in the past. Black hole mergers in particular leave long-term marks on the universe's structure. When two supermassive black holes combine, they may receive a gravitational kick, sending them moving through their host galaxy or even the cluster. The motion of such hypermassive black holes disturbs surrounding stars and gas, changing orbital patterns and triggering new waves of star formation or star ejection. Over millions of years, these effects accumulate, influencing how galaxies settle into new shapes, how clusters arrange themselves, and how energy flows through cosmic filaments connecting clusters across hundreds of millions of light years. The chemical consequences of long-term collisions are equally dramatic. Supernovae triggered by collision-driven star formation distribute heavy elements into the interstellar medium. Black hole jets heat gas, preventing some regions from collapsing, while allowing others to form new stars enriched with heavier elements. These processes seed future planetary systems with the ingredients for rocky worlds, metals, and even the building blocks for life. In this way, cosmic collisions indirectly influence the chemistry of galaxies and eventually the environments where life might emerge. Even though life on Earth is unlikely to be directly affected, the echoes of these events travel across the cosmos. Gamma-ray bursts, X-ray emissions, and gravitational waves reach across billions of light years, carrying the story of massive collisions. Telescopes detect them as faint signals, but they are the whispers of events that reshaped galaxies, triggered star formation, and created black holes more massive than anything in our galaxy. Each detection tells us that the universe is alive with energy and motion, and that even events far from us leave a trace that can be measured, studied, and imagined. Long-term impacts are visible in galaxy evolution, cluster dynamics, and cosmic structure. Tidal tails, new star clusters, supermassive black holes, and compressed gas clouds all trace the path of past collisions. Shockwaves fade, but the rearrangement of stars, gas, and dark matter continues to shape the universe. Over billions of years, repeated collisions build larger galaxies, more massive black holes, and larger clusters, creating the web of filaments and voids that defines the cosmic landscape. The universe is constantly sculpted by these forces, a dynamic system where past events echo across space and time. Even the most violent events ultimately contribute to creation as well as destruction. Collisions compress gas, trigger star formation, and seed galaxies with new stars and heavy elements. Black hole mergers reorganize clusters, shaping the gravitational backbone of the universe. Shockwaves fade, but their effects ripple through star-forming regions, leaving lasting consequences for billions of years. In every corner of space, from the cores of colliding galaxies to the outskirts of clusters, the legacy of past collisions is visible, creating the patterns, structures, and chemistry of the universe we see today. Solar system versus galaxy collision. When we think about collisions in space, it's tempting to imagine something crashing in the sky, like an asteroid hitting Earth. That's dramatic enough for us to grasp the explosion, the energy, the impact on our planet. But it's tiny. The energy released by an asteroid impact is minuscule compared to even the smallest cosmic collisions. A massive asteroid might release energy comparable to 1 million nuclear bombs. The total energy of the Sun over a single second is vastly more, and the energy in a supernova explosion dwarfs that. But even that pales in comparison to what happens when galaxies collide. A collision within our solar system is tiny on a cosmic scale. Planets are separated by millions or billions of kilometers, and even the largest objects, Jupiter, Saturn, are minuscule compared to the distances between stars. An asteroid or comet impact on a planet releases enough energy to reshape a planet's surface, but it doesn't affect the Sun or neighboring stars in a meaningful way. If the Sun were to collide with a rogue star, that would be enormous by solar system standards. But the Sun is still just a single star. Its energy output is massive to us, but to a galaxy, it's a drop in the ocean. Now scale up to a galaxy collision. A single spiral galaxy like the Milky Way contains hundreds of billions of stars, clouds of gas and dust, massive black holes at the center, and invisible dark matter holding everything together. The mass of the Milky Way is over 1 trillion times the mass of the Sun, and when it collides with another galaxy like Andromeda, the energies involved are unimaginable. Stars mostly pass by each other because of the distances between them, but the gas clouds slam together at thousands of kilometers per second. Shockwaves ripple through the interstellar medium, heating gas to millions of degrees, triggering bursts of star formation, and feeding central supermassive black holes. The total energy released in such collisions is trillions of times higher than anything the solar system could ever produce. Timescales are another staggering difference. An asteroid strike might happen in seconds, with after effects lasting years, maybe centuries, for planetary geology. A supernova explosion in a nearby star lasts weeks to months visibly, and its shockwave travels across a few light years. But galaxy collisions unfold over hundreds of millions of years. When the Milky Way and Andromeda merge, the initial approach, gravitational interaction, and eventual coalescence of their cores will take roughly 4.5 billion years. Stars orbiting the galactic center are flung into new paths slowly. Tidal tails stretch for millions of light years, and shock-heated gas cools over hundreds of millions of years. The solar system is like a firecracker compared to the slow, grinding evolution of galaxies merging over cosmic timescales. Energy comparisons make your head spin. The total kinetic energy in two colliding galaxies, considering stars, gas and dark matter, can reach roughly 10 to the power of 58 to 10 to the power of 60 ergs. To put that in perspective, the Sun produces roughly 10 to the power of 33 ergs per second. That means the energy in a single galaxy collision equals the Sun's lifetime output multiplied by billions of billions. A supernova explosion is around 10 to the power of 51 ergs. A galaxy collision releases energy millions of times more than a supernova, and this energy is spread over shock waves, star formation, and central black hole accretion rippling across millions of light years. Scale comparisons are just as dramatic. A solar system collision is local. Planets, asteroids, maybe the Sun. A galaxy collision involves hundreds of billions of stars, enormous clouds of gas spanning tens of thousands of light years, and dark matter halos stretching hundreds of thousands of light years. The distances between stars in a galaxy mean that while they rarely collide directly, the collective gravitational forces reshape everything. Galaxy clusters amplify this. When clusters collide, millions of stars, countless black holes, and enormous clouds of hot gas interact over millions of light years, with shock waves propagating at thousands of kilometers per second across volumes larger than any single galaxy. The solar system is microscopic in comparison. Planets, moons, and comets look like specks when placed against the scale of galactic collisions. Timescales also highlight differences in human perception versus cosmic reality. A meteor impact can be dramatic in a day or a year. A supernova is dramatic over months to years. But galaxies take hundreds of millions of years to finish a merger. Even if two stars pass dangerously close during a collision, the odds of direct impacts are low, but the gravitational influence is enough to eject stars into intergalactic space. Tidal tails stretching for hundreds of thousands of light years form slowly, yet they persist for billions of years, leaving permanent marks on the galaxy's shapes. Energy is released slowly across these timescales, unlike the sudden burst of a supernova or asteroid strike, but the total effect is far greater, shaping entire clusters of galaxies and even cosmic filaments. Observing these differences in energy, scale, and time helps us appreciate the true magnitude of cosmic collisions. Gravitational wave detections capture short bursts from black hole mergers, lasting seconds to minutes, but they carry energy trillions of times more than a solar system impact. X-ray images of cluster collisions show shock-heated gas stretching millions of light years, revealing energy scales far beyond what any local event could produce. Infrared telescopes like JWST capture star formation bursts triggered by collisions, showing hundreds of thousands of new stars forming over millions of years. Each tool gives a glimpse into a different scale, energy level, or time scale, and together they illustrate how small our solar system is compared to these galactic events. Even computer simulations reveal the contrast in a way we can visually grasp. A solar system impact is easy to model in seconds or minutes on a screen, asteroids colliding, planets shifting, debris flying. Galaxy collision simulations require supercomputers tracking billions of particles over millions of years. The resulting visualizations show stars stretching into tails, shockwaves glowing across interstellar gas, and central black holes merging over hundreds of millions of years. Time is compressed in the simulation, but the energy flows, mass rearrangements, and structural transformations are staggering. The difference between simulating a solar system scale event and a galaxy scale event is like comparing a firework to a continent-wide storm unfolding over millions of years. Scale also affects observable consequences. A solar system collision might change a planet, produce craters and send debris flying, but it doesn't alter the galaxy's structure. Galaxy collisions redistribute mass, trigger star formation, reshape spiral arms, feed black holes, and can even send galaxies careening into new trajectories within a cluster. Cluster collisions amplify this effect, producing shock waves that heat gas to tens of millions of degrees, altering the dark matter distribution and affecting nearby filaments. The immediate energy is huge, but the long-term rearrangement of structure is even more staggering. The solar system impact is tiny by comparison, local chaos without cosmic consequences. Even radiation output scales dramatically. A solar flare or supernova might produce radiation that affects planets nearby. Galaxy collisions generate energy visible across millions of light years. Shock-heated gas radiates in X-rays. Newly formed massive stars emit ultraviolet light, and accretion onto central black holes generates high-energy jets visible across the universe. Gamma-ray bursts from massive star collisions triggered during these events could, in principle, be detected across galaxies. Energy from these collisions is not just local, it ripples across space, shaping the universe itself. Gravitational interactions also scale differently. In the solar system, gravity is dominated by the Sun. Planets influence each other weakly, and collisions are rare and mostly local. In galaxy collisions, gravity acts across millions of light years. Stars, gas, and dark matter all respond collectively. Tidal forces twist galaxies, eject stars, and compress gas clouds. Dark matter halos guide the motion of visible matter, shaping collisions in ways that have no analogue in a single planetary system. The energy stored in these gravitational interactions is vast, and the timescale over which it is released, hundreds of millions of years, is unimaginable compared to planetary collisions. Even thinking in numbers is mind-boggling. The Milky Way has a mass of about 1.5 trillion suns, and Andromeda slightly more. Their relative velocity toward each other is over 110 kilometers per second. The kinetic energy of just their motion is orders of magnitude larger than any solar system impact. When these galaxies merge, gas collides at thousands of kilometers per second, forming shocks that heat gas to millions of degrees and trigger star formation. Black holes in the cores interact, merge, and release energy via gravitational waves that can be detected across billions of light years. The scale is beyond comprehension, and yet it is all happening right in the universe we live in, slowly shaping the future of galaxies, clusters, and filaments. The contrast is even more vivid when you compare timescales with human experience. A meteor strike is sudden and dramatic. A solar flare can affect satellites in hours. Supernovae last weeks to months. Galaxy collisions unfold slowly over hundreds of millions of years, with tidal tails stretching for tens of thousands of light years, star formation bursts happening across millions of years, and black hole mergers slowly reshaping cluster centers. Energy is released gradually, distributed across enormous distances, yet the cumulative effect is universe-changing. Milky Way Andromeda collision versus galaxy cluster collisions. When you think about the Milky Way and Andromeda heading toward each other, It sounds like a dramatic cosmic crash, and it is. But in terms of energy and scale, it's tiny compared to collisions between galaxy clusters. The Milky Way is massive, about 1.5 trillion times the mass of the Sun, and Andromeda is even bigger, holding over 2 trillion solar masses. Their collision will stretch across hundreds of thousands of light years, twisting spiral arms into long streams of stars and gas. Gas clouds will slam together at hundreds of kilometers per second, triggering bursts of star formation. The supermassive black holes at their centers will eventually meet, sending ripples of gravitational waves across the universe. Even so, compared to a galaxy cluster collision, it's like a pebble hitting a mountain. Galaxy clusters contain hundreds or thousands of galaxies, trillions of stars, enormous clouds of hot gas, and massive dark matter halos that extend millions of light years. When two clusters collide, it's not just a few spiral galaxies interacting, it's entire cities of galaxies smashing past each other, with gas heating up to tens of millions of degrees, producing X-rays and shock waves that stretch across millions of light years. The energy released in these cluster collisions is huge, far beyond what even the Milky Way Andromeda collision can produce. The differences in speed are also massive. Stars in the Milky Way and Andromeda will interact mostly through gravity, with gas clouds colliding at hundreds of kilometers per second. In cluster collisions, entire clouds of gas and galaxies move at thousands of kilometers per second. Shock waves expand across the intergalactic medium, heating gas to extreme temperatures and compressing it into filaments. These filaments become sites for star formation and can stretch millions of light years, linking clusters along the cosmic web. The Milky Way Andromeda collision will reshape two galaxies over billions of years, but a cluster collision transforms entire regions of space in a shorter cosmic time. Another big difference is scale. The Milky Way Andromeda collision will affect two galaxies across about 200,000 light years, with tidal tails extending maybe a few 100,000 light years. Cluster collisions involve structures tens of millions of light years across. Gas clouds hundreds of thousands of light years wide slam into each other, creating enormous shock fronts. Dark matter guides the motion of galaxies, while the visible gas and stars interact and produce huge bursts of radiation. Observations like the Bullet Cluster and El Gordo show gas glowing in X-rays across millions of light years, with galaxies and dark matter moving past the shocks almost independently. It's hard to even picture, but these collisions are on a scale hundreds of times bigger than Milky Way Andromeda. Energy release is another way to see the difference. The kinetic energy in the Milky Way Andromeda collision is huge by our standards, more than all the energy the Sun will produce over its lifetime. Stars will mostly pass by each other, but gas will heat up and ignite star formation. Now think of two clusters colliding. El Gordo is moving at roughly 2,000 kilometers per second. The energy involved in gas heating alone is billions of times larger than the Milky Way Andromeda collision. Shock waves ripple through intergalactic gas, compressing it and creating new stars in massive bursts. The collision also rearranges dark matter, shaping the future gravitational structure of the universe. Timescales are similar, but feel different because of the scale of mass and distance. The Milky Way Andromeda collision will take billions of years, stars gently shifting orbits, spiral arms twisting and merging, gas clouds slowly colliding and central black holes spiraling toward each other. Cluster collisions happen faster in relative terms. Two clusters approach at thousands of kilometers per second. Gas slams together, shock waves expand, and the larger scale structures are altered in tens to hundreds of millions of years. It's a shorter but more violent process, reshaping huge volumes of space almost immediately compared to the slow dance of two spiral galaxies. Another key difference is what happens to star formation. In the Milky Way Andromeda collision, star formation will be noticeable, concentrated in compressed gas clouds, but only in limited regions compared to the enormous scales of clusters. Cluster collisions create star formation across millions of light years as gas filaments collapse under shock compression. Some of the biggest bursts of star formation in the universe occur in cluster collisions, lighting up thousands of new stars across multiple galaxies. The sheer scale of energy, distance, and number of galaxies involved makes it a cosmic event far beyond anything our galaxy alone could produce. Observationally, we see the difference in detail. Hubble and Chandra images of merging galaxies like the Antenna or the Milky Way Andromeda collision simulations show twisting spiral arms, star clusters forming in gas clouds, and tidal tails extending far into space. When we look at clusters, X-ray images reveal enormous shock fronts and hot gas stretching millions of light years, with hundreds of galaxies embedded in the chaos. Gravitational lensing maps show dark matter moving independently of the visible gas, confirming that cluster collisions are on a scale far bigger than two galaxies merging. Even in simulations, the contrast is clear. Modelling Milky Way Andromeda is complicated but manageable on standard supercomputers. Modelling cluster collisions requires billions of particles, tracking dark matter, gas, and stars over millions of years. Visualizations show gas clouds stretching, compressing, and heating, galaxies moving past each other, and shockwaves expanding across huge volumes. The scale of motion and energy is huge, literally hundreds of times bigger than galaxy-to-galaxy collisions. One more difference is the effect on the cosmic web. Milky Way Andromeda affects local space, maybe changing nearby satellite galaxies, maybe forming new star clusters. Cluster collisions affect filaments and structures across tens of millions of light years, influencing how future clusters and galaxies form and evolve. They redistribute gas and dark matter across the cosmic web, shaping large-scale structure for billions of years. The Milky Way Andromeda collision is impressive, but in the grand scale of the universe, it's a small drama compared to the huge events happening in cluster collisions. Even in terms of black holes, the difference is massive. The central black holes of Milky Way and Andromeda may merge to form a supermassive black hole at the center of the new galaxy, releasing detectable gravitational waves. In cluster collisions, multiple galaxies with supermassive black holes interact. Central black holes feed on massive amounts of gas from disrupted galaxies, merge, and create enormous gravitational waves and high-energy jets, impacting the cluster environment over millions of light years. The scale of energy and influence is huge compared to a single galaxy merger. The consequences for star formation and cosmic evolution also scale up. Milky Way Andromeda will trigger new stars in dense gas clouds, but cluster collisions create bursts across whole regions of clusters, changing the structure of multiple galaxies simultaneously. Shockwaves heat the intergalactic medium, compressing gas and forming filaments along the cosmic web. Over billions of years, this shapes the future of galaxy clusters, creating new paths for star formation and influencing dark matter distribution. In a way, galaxy mergers are like painting one galaxy, while cluster collisions redraw the canvas for millions of galaxies at once. Even the way we observe them highlights the scale difference. Galaxy collisions are mostly visible in optical, infrared, and ultraviolet light, tracing new stars and tidal tails. Cluster collisions are visible in X-rays from hot gas, radio from cosmic jets, and gravitational lensing from dark matter. Shockwaves stretch across millions of light years and glow for billions of years, while the Milky Way Andromeda collision's main fireworks are confined to a few 100,000 light years. The energy, distance, and effect are huge. Hypergiant star explosion versus black hole merger. Imagine a single star dying in a colossal explosion, a hypergiant star like VY Canis Majoris or UY Scuti reaching the end of its life. These stars are already hundreds or even thousands of times larger than the Sun, their mass tens of times greater. When one of these giants collapses, it doesn't just vanish quietly, it erupts as a supernova, or in the most extreme cases, a hypernova, sending energy blasting into space at unimaginable speeds. The explosion releases more energy in a few seconds than our Sun will produce in its entire 10 billion year lifetime. Gamma-ray bursts shoot across the galaxy, beams of high-energy radiation traveling at nearly the speed of light, ripping through gas clouds, ionizing atoms, and lighting up the universe. For a sense of scale, the energy released in one of these explosions could power all human civilizations for trillions of years. Every particle of gas in the vicinity is pushed, compressed, and heated, triggering shock waves that can collapse nearby clouds into new stars. Now compare that to a black hole merger. Two supermassive black holes, millions or billions of times the mass of the Sun, spiral toward each other in a slow, deadly dance. As they merge, they send ripples through the very fabric of space-time itself, gravitational waves that travel across billions of light years. The energy released is so huge that it outshines hypergiant explosions by orders of magnitude. In fact, a single black hole merger can release more energy in gravitational waves than all the stars in a galaxy combined emit in light over millions of years. It's hard to even imagine. If we tried to measure that energy in human terms, it could power every human civilization that has ever existed, for not just trillions, but potentially quadrillions of years. The waves themselves stretch and squeeze space as they pass, altering distances between stars, though only by tiny amounts we can detect with instruments like LIGO and Virgo. The visual difference is dramatic. A hypergiant star explosion is bright, colourful, chaotic. Gas clouds are blasted apart, glowing in X-rays, ultraviolet, and visible light. Jets shoot out along the star's poles, gamma rays flare across interstellar distances, and newly formed elements like gold, iron, and uranium scatter into the galaxy. It's violent, brilliant, and short-lived, seconds to minutes of maximum intensity, then fading over weeks to months. By contrast, a black hole merger is invisible in light. You can't see it with your eyes, or even with traditional telescopes. Its violence is measured by the ripples it makes in space-time and the energy it imparts to nearby gas or stars. The impact is subtle in appearance, but immense in power. Timescales differ too. A hypergiant star explosion happens almost instantly on cosmic scales. The collapse of the core, the rebound of the outer layers, and the gamma-ray jets are all over in seconds. The afterglow, the expanding supernova remnant, glows for years to decades, but the peak energy is immediate. Black hole mergers are slower, especially for supermassive black holes. They spiral toward each other over millions of years, feeding on surrounding gas, gradually accelerating as they approach. The final collision, the moment of merger, lasts minutes to hours. But the energy is released in a way that travels across billions of light years almost instantly. The scale of destruction also varies. A hypergiant star explosion can wipe out nearby planets in its own galaxy if the gamma-ray burst is aimed at them. It shapes surrounding gas clouds, triggers star formation, and spreads heavy elements across space. A black hole merger can rearrange entire galactic centers. Gas clouds are disturbed, stars are thrown into new orbits, and the gravitational impact can reshape the paths of surrounding galaxies in a cluster over millions of years. Both are destructive, both are creative, but the black hole merger operates on a much bigger scale. The energy itself is almost incomprehensible. A single hypergiant supernova might release about 10 to the power of 46 joules. That's enough to power all human civilization for trillions of years. A black hole merger, especially supermassive ones, can release more than 10 to the power of 56 joules in gravitational waves alone. That's beyond trillions, millions of trillions of years' worth of human energy, all compressed into a single cosmic event. And it doesn't stop there. The ripples in space-time from a black hole merger pass through the universe, invisible but measurable, carrying energy across billions of light-years, affecting the cosmic fabric itself. Even nearby, effects feel different. Hypergiant explosions blast surrounding gas, compressing clouds to form new stars. They produce shock waves that move at thousands of kilometers per second, heating the interstellar medium to millions of degrees. Black hole mergers can heat gas indirectly, pulling matter into accretion disks that release energy as X-rays or jets along their poles. The difference is, one is explosive and colourful. The other is invisible yet enormous, bending space itself. Simulations help us visualize this. In a supercomputer rendering of a hypergiant star explosion, you see layers of gas blowing outward in all directions, glowing and fragmenting, gamma-ray jets streaming along the poles. Shockwaves compress neighbouring clouds, sparks of star formation flare along the edges. In simulations of black hole mergers, you can't see the black holes themselves, but ripples in space-time distort grids around them. Stars accelerate in new orbits, gas swirls in accretion disks, and jets shoot out from the merged core. The energy flows across scales unimaginable in everyday life. Both events also leave lasting legacies. Hypergiant explosions seed the galaxy with heavy elements, providing material for future stars and planets. Black hole mergers change the structure of galaxies and clusters, influencing star formation and the orbits of billions of stars over millions of years. One is short, bright and deadly in a local region. The other is long, invisible, and shapes the universe itself. But in terms of raw energy, the black hole merger wins by orders of magnitude, releasing enough energy to dwarf entire stellar populations, to stretch space-time, and to echo across the universe. Future collisions we know are coming. If you look at the night sky tonight, the stars seem calm, serene, almost frozen in place. But out there, millions of light years away, an immense, silent drama is already underway. Our galaxy, the Milky Way, is on a slow-motion collision course with its giant neighbour, the Andromeda Galaxy. Over the next 4.5 billion years, these two massive spiral galaxies will approach each other, drawn together by gravity, spiralling faster and faster as they close the gap. From our perspective, it's unimaginable, but from the universe's view, it's a slow but huge smash-up waiting to happen. Andromeda is bigger than the Milky Way, with more than 2 trillion times the mass of the Sun, compared to our galaxy's roughly 1.5 trillion solar masses. That mass doesn't just sit there quietly. Gravity stretches across hundreds of thousands of light years, pulling stars, gas, and dark matter toward each other. The initial approach will distort the outer spiral arms, tugging them into long, sweeping tidal tails that stretch far beyond the main disks of either galaxy. Stars will shift slightly in their orbits, and massive clouds of gas will collide at hundreds of kilometers per second, igniting bursts of new star formation that will light up the galaxies like fireworks. We know the general timeline thanks to decades of observation and simulation. Andromeda is approaching at about 110 kilometers per second, and in cosmic terms, that's fast. But space is vast. It will take billions of years before the first significant encounter, and even then, the galaxies won't slam directly into each other. Most stars will pass by without colliding, but the gas, dust, and dark matter won't be so lucky. Gas clouds will crash together, heating to millions of degrees and producing massive shock waves. New stars will ignite in clouds compressed by the collisions, some forming massive hypergiants that will live short, violent lives before exploding as supernovae. As the two galaxies continue their dance, their supermassive black holes, Sagittarius A star at the center of the Milky Way and Andromeda's central black hole, will slowly spiral toward each other. Eventually, they will merge, releasing gravitational waves powerful enough to ripple across billions of light years, bending space-time as they combine into a hypermassive black hole. This process will inject energy into surrounding gas, potentially triggering more star formation or ejecting matter from the newly merged galaxy's core. Over the billions of years it takes for the merger to settle, the galaxies will reshape entirely, forming a giant elliptical galaxy, sometimes nicknamed Milkomeda by astronomers. The consequences won't be limited to the galaxies themselves. Our solar system, tucked away in one of the Milky Way's spiral arms, might survive the collision intact, or it might be flung into a new orbit hundreds of thousands of light years from the new galactic core. The night sky from Earth, or whatever remains of it billions of years from now, will light up with thousands of new stars formed from the collision's triggered starbursts, creating a cosmic spectacle unlike anything we see today. But the Milky Way Andromeda collision is only the beginning. On a much larger scale, the local group, our small galaxy cluster, is moving within the Laniakea supercluster, a massive structure of galaxies, clusters, and filaments spanning over 500 million light-years. Over the next tens of billions of years, the dynamics of these superclusters will continue to evolve. Gravity will slowly pull smaller galaxy groups into larger ones. Galaxy clusters will merge, forming even more massive structures. Our local group might eventually collide with the Virgo cluster, triggering a huge intergalactic ballet on scales that dwarf even the Milky Way Andromeda collision. Simulations of these future events are mesmerizing. Supercomputers can model billions of particles representing stars, gas, and dark matter, showing how gravity reshapes the universe on immense scales. Streams of stars will stretch across millions of light years. Entire clusters of galaxies will compress, and shock waves from intergalactic gas collisions will heat clouds to tens of millions of degrees. The energy released in such events is beyond imagination, trillions of times more than all the energy the Sun will produce in its lifetime. And yet, it unfolds slowly over billions of years, giving space the illusion of calm, while it is anything but. The Milky Way Andromeda collision will produce regions of chaos and beauty. Gas clouds compressed in the galactic cores will feed star formation and black hole growth, while tidal tails fling stars into intergalactic space. Some stars may be ejected entirely from the new galaxy, wandering alone through the void. The combined black holes at the center will dominate the new galactic core, shaping the orbits of billions of stars. Over billions of years, the remnants of this collision will settle into a massive elliptical galaxy, calm in appearance, but built from centuries of violent interactions. On the supercluster scale, the effects are even more dramatic. When clusters collide, gas heats to extreme temperatures, observable in X-rays, while galaxies continue their motion almost independently. Gravitational interactions pull clusters together over millions of light years, reshaping filaments of the cosmic web. Dark matter guides these motions invisibly, ensuring that while the visible matter crashes and twists, the underlying structure of the universe remains coherent, yet transformed. Future collisions among superclusters will slowly redistribute mass across the universe, changing where galaxies form, how clusters move, and even how dark matter threads through space. The timeline is immense. The Milky Way Andromeda collision unfolds over roughly 4.5 billion years. The fate of superclusters stretches over tens of billions of years. The energy involved scales up accordingly. While a galaxy merger might release energy equivalent to trillions of suns in kinetic and thermal energy, cluster and supercluster mergers release energies orders of magnitude higher. Gas clouds, millions of light years across, collide at thousands of kilometers per second. Shock waves ripple across vast distances, and gravitational energy reshapes entire regions of the universe. The scale of destruction, creation, and transformation is huge. Even the observable consequences are mind-blowing. The night sky, billions of years from now, won't resemble anything we know. Stars will form in dense knots of gas. Supernovae will explode in brilliant flashes. Black holes will emit high-energy jets, and tidal tails will stretch across distances we can barely imagine. Light from newly formed stars will illuminate regions of space that are today dark, while the gravitational framework of clusters and superclusters will continue to pull galaxies into new arrangements. These are cosmic events that happen too slowly for humans to witness in full, yet the signs are visible across the universe in the form of galaxy shapes, cluster distributions, and X-ray emissions. Gravitational waves will echo across billions of light years. The merger of Milky Way and Andromeda's central black holes will release energy so huge that it briefly outshines all the stars in both galaxies combined. On a supercluster scale, multiple black hole mergers in colliding clusters will produce waves detectable across the observable universe, carrying energy and information about the most massive objects interacting in space. These ripples are the universe's way of letting us hear collisions that are otherwise invisible, a cosmic symphony playing out over billions of years. In simulations, we can see how the local universe will transform. The Milky Way and Andromeda spiral into each other, arms twisting, gas clouds colliding, black holes merging. On larger scales, clusters collide, shockwaves expand, and filaments of the cosmic web stretch and compress. Gas heats, cools, and reforms into stars. Galaxies are flung into new orbits, sometimes leaving trails of stars that become new dwarf galaxies or isolated star clusters. The energy is huge, the scale is huge, and the timescale is beyond anything human imagination can fully grasp. Even for life on Earth, these future collisions are unlikely to pose a direct threat. Gamma-ray bursts from hypergiant stars triggered in these collisions, or radiation from black hole accretion, could in theory reach distant planets. But the odds are tiny. Instead, the universe is reshaped slowly, on scales that make human time feel like seconds. Our Sun might be ejected into a new orbit in the merged galaxy. The solar system carried along in a massive interstellar dance, witnessing new stars forming, new black holes feeding, and entire regions of space glowing with the energy of creation and destruction. The Milky Way Andromeda collision is a local preview of the larger fate of our supercluster. Just as two spiral galaxies merge over billions of years, galaxy groups and clusters will collide, merging into larger and larger structures. Filaments of the cosmic web will realign, dark matter will redistribute, and the universe's large-scale structure will slowly transform. Over tens of billions of years, the local group may join with Virgo, and eventually local superclusters may collapse under gravity into even larger, denser structures, leaving the rest of the universe expanding around them, isolated in enormous voids. The visual spectacle is incredible to imagine. Streams of stars twisting across hundreds of thousands of light years, tidal tails forming new star clusters, supernovae flashing across space, X-ray glowing clouds of gas stretching millions of light years, jets from black holes feeding on colliding gas. This is the universe in motion, not static, not calm. Every future collision leaves its mark, shaping galaxies, clusters, and superclusters, rewriting the cosmic landscape and redistributing energy and matter across the observable universe. How astronomers predict these events. From here on Earth, it's easy to think the night sky is frozen, that stars and galaxies sit quietly in their spots. But in reality, the universe is constantly moving, and astronomers have become experts at reading that motion like a cosmic clock. Predicting collisions like the Milky Way and Andromeda requires careful observation of how galaxies move across space, how fast they're heading toward or away from us, and what forces are shaping their paths over billions of years. One of the first clues comes from measuring velocity through redshift and blueshift. Light from an object moving toward us compresses, shifting toward the blue end of the spectrum, blueshift. Light from objects moving away stretches, shifting toward red, redshift. By carefully analysing the light from Andromeda, astronomers discovered it is moving toward the Milky Way at about 110 kilometres per second. That's incredibly fast by everyday standards, and it immediately told scientists that a collision is inevitable, though it will take billions of years to happen. But velocity alone isn't enough. Galaxies also move through space in 3 dimensions, not just directly toward or away from us. Astronomers track their proper motion, how they drift across the sky relative to distant background stars. For Andromeda, this motion is small but measurable using highly precise instruments like the Hubble Space Telescope. By combining the line of sight velocity from redshift/blueshift with proper motion across the sky, scientists can map its true path. That's how they know it isn't missing us entirely or just grazing past. We are set on a slow-motion crash course. Simulations play a huge role in turning these measurements into predictions. Astronomers feed data on galaxy mass, star distribution, gas content, and dark matter into supercomputer models, then let gravity take over. The models predict how galaxies spiral toward each other, how their disks warp, and how tidal tails form. They also show how gas clouds collide, trigger star formation, and feed central black holes. The combination of observations and simulations allows astronomers to foresee not just that a collision will happen, but exactly how it will unfold over billions of years. Observing clusters and superclusters works similarly. Redshift maps from surveys like the Sloan Digital Sky Survey measure the motion of thousands of galaxies at once. Clusters moving toward each other show blueshift. Clusters moving apart show redshift. Combining these measurements with the galaxy's positions and mass estimates allows astronomers to predict future mergers and understand how large-scale structures in the universe will evolve. They can tell which galaxy groups will collide in the next billion years, how gas will heat up in shock waves, and where star formation will be triggered. Dark matter complicates things, but astronomers have clever ways to account for it. By studying gravitational lensing, how light from distant galaxies bends around massive objects, they can map the invisible mass in clusters and superclusters. That mass affects the motion of galaxies and the timing of future collisions. Without accounting for dark matter, predictions would be wildly inaccurate. With it, simulations match observations and show us the slow, precise dance of galaxies across the cosmos. Even supermassive black holes give clues. Astronomers track their motion indirectly by observing the stars and gas in galactic cores. If 2 galaxies are approaching, their central black holes are destined to meet eventually. Simulations show how they spiral inward, how gravitational waves will ripple across space-time, and how energy from their accretion will light up the surrounding gas. Combining velocity measurements, mass estimates, and computer models makes it possible to see the endgame of these cosmic collisions long before they happen. Visualizing these predictions is dramatic. Astronomers can produce animations showing the Milky Way and Andromeda twisting together over billions of years. Stars move along curved paths, spiral arms stretch into tidal tails, and shockwaves race through gas clouds. The simulations are based entirely on observed motion, redshift/blueshift data, and gravitational physics. Each flicker on the screen is grounded in real measurements, showing the universe in motion, not frozen in the night sky. Even for local superclusters, astronomers use these techniques to predict massive future collisions. The local group, the Virgo cluster, and surrounding filaments are mapped with precision. Galaxy velocities, dark matter distributions, and redshift measurements allow scientists to see which clusters are slowly moving toward each other. They can forecast collisions, mergers, and the rearrangement of filaments over tens of billions of years. These predictions show the cosmic future in vivid detail, letting us watch the universe reshape itself on mind-blowing scales, long before it actually happens. What simulations suggest will happen to stars, planets, black holes, and gas? Imagine a universe in motion, where entire galaxies spiral toward each other over billions of years. Supercomputers running simulations of these colossal events show a chaotic, beautiful, and violent dance unfolding on scales that dwarf the imagination. Stars, planets, black holes, and gas all move and interact under gravity's invisible hand, reshaping galaxies and lighting up the cosmos. Let's start with the stars. In galaxy collisions like the Milky Way and Andromeda, simulations show that most stars never collide directly. They're far apart, separated by light years, but their paths are wildly distorted. Spiral arms stretch and twist, forming long, curving tidal tails that fling stars far into intergalactic space. Some stars are captured by the other galaxy, changing orbits entirely. Others are ejected, sent hurtling alone through the void at hundreds of kilometers per second. Over billions of years, the simulations reveal a universe of stars shifting like particles in a cosmic whirlpool, some finding themselves in dense clusters where new stars will ignite, others wandering alone forever. Planets face a similar fate, but on a smaller scale. Around their stars, they're mostly safe, as direct stellar collisions are rare. Yet simulations suggest that gravitational chaos can fling entire solar systems into new orbits. The solar system might be nudged closer to the new galactic center or slingshot into a far-flung spiral arm, exposing planets to different radiation levels or stellar neighborhoods. Some planets may even be ejected entirely, becoming rogue planets drifting alone in intergalactic space. These simulations give a sense of cosmic scale, billions of stars and planets slowly reshaping their positions over billions of years, in a dance that seems graceful from afar, but is violent up close. Black holes are the true powerhouses in these simulations. Supermassive black holes at the centers of colliding galaxies spiral toward each other in slow, inevitable orbits. As they approach, they stir surrounding gas, forming luminous accretion disks that feed on matter drawn inward by gravity. Simulations show these disks glowing in X-rays and other high-energy light, while jets of plasma shoot out along the poles, spreading energy across hundreds of thousands of light-years. When the black holes finally merge, gravitational waves ripple through space-time itself, carrying energy across billions of light-years. The simulations show the resulting hypermassive black hole at the center of the new galaxy, a silent but dominant engine around which billions of stars orbit in reshaped patterns. Gas clouds are some of the most dramatic elements in these simulations. Unlike stars, they collide directly, compressing, heating, and sparking bursts of star formation. Massive clouds slam together at hundreds of kilometers per second, heating to millions of degrees, creating X-ray glowing shockwaves visible across space. Simulations show these collisions forming dense knots of gas where new stars ignite, some massive enough to become hypergiants that live short, violent lives before exploding as supernovae. Streams of gas can also be expelled from the galaxy entirely, trailing in long filaments or feeding intergalactic space. The visualizations are breathtaking. Swirling clouds of gas lighting up in brilliant flashes as they compress, fragment, and ignite new stellar generations. Simulations also reveal cascading effects. The collision of stars and gas can trigger starbursts in entire regions of the galaxies, lighting up the universe with thousands of new stars forming simultaneously. Black holes grow as they consume gas funneled into galactic centers, their gravitational influence reshaping stellar orbits for millions of years. Gas ejected into tidal tails or compressed in filaments continues to form stars far from the galactic cores, creating a universe where matter is constantly moving, reshaping, and creating new structures. Time in these simulations is mind-boggling. Each frame represents millions of years, yet the motion is continuous, a slow-motion ballet of chaos and creation. Stars trace curved arcs, spiral arms collide and fold, black holes dance toward inevitable mergers, and gas flows, ignites, and spreads across vast distances. The results are visually stunning, with tidal tails stretching hundreds of thousands of light years, gas clouds glowing in X-rays, and jets from black holes carving through the cosmos. Every frame is grounded in gravity, mass and energy physics, yet the spectacle feels almost alive. Simulations even explore extreme scenarios. Some stars are flung at speeds high enough to leave the merged galaxy entirely, becoming intergalactic nomads. Some gas clouds compress into massive clumps that might form entire new dwarf galaxies. Supermassive black hole mergers produce gravitational waves detectable across billions of light years, bending space-time like ripples across a cosmic pond. These extreme events, while rare, are part of what makes galaxy collisions so fascinating. They reshape everything, from individual stars to the larger structures in the universe. The interplay between stars, planets, black holes, and gas also creates incredible contrasts. Stars provide structure and light, moving along distorted paths. Planets mostly follow stars, sometimes getting flung into new regions of the galaxy. Black holes dominate the center, controlling energy flow and gravitational order. Gas is chaotic, colliding, heating, cooling, and forming new stars. Simulations show these elements together in a cosmic storm, each responding differently to gravity, each contributing to the final shape of the merged galaxy. Even the tiniest details are captured. Gas compression can trigger specific star formation rates, determining how many massive stars ignite, how supernovae spread heavy elements, and how the next generation of stars will form. Black holes' accretion disks glow in X-rays and gamma rays, sending energy into surrounding gas that can either trigger or suppress star formation depending on the local environment. Stars can cluster in new groups or scatter across the galaxy. Every particle, from gas cloud to rogue star, is tracked in these simulations, giving astronomers a detailed look at the chaotic beauty of galactic evolution. Observationally, these simulations are confirmed by images from Hubble, Chandra, and the James Webb Space Telescope. The twisting arms of colliding galaxies, bright knots of star formation, glowing X-ray gas, and massive black hole jets all match predictions from simulations. This synergy between observation and modelling allows scientists to see the future, to predict the fate of galaxies, their stars, planets, black holes, and gas with astonishing accuracy.